Let's see how it runs with OBS running. Have I left it in a debug mode where the ground is flat? Yeah, I think I've left some kind of debug thing. Let me check the code. That's dumb. That's very dumb of me. Let's see, the ground is here. Looks alright. Doesn't look like I've commented anything out here. Let's see. Nope. Okay. Has height variation, clearly. I just was forgetting. Oh, this one has no height variation, but this has height variation. And the problem is I've changed these. Oh, shoot. I don't know which way I'm looking. There we go. Okay. Yeah, I've changed these colors to be very desaturated so that I could make a nice screenshot for the trees to show to the guy who made the trees. And then I never changed it back to more contrasty. But so anyway, how fast is it running? Not very fast, but that's fine. It's fast enough for demoing. So what's our time? Oh, I can't move my mouse to the bottom because I'm using crappy simple input controls. 1:33. Okay, good time to start. So, hi, hello. We'll talk about pretty much everything you see here. Here's one thing to see is at the very center, there's a bug that I fixed once, and then I never went back and fixed this weird column that flickers. And since this is downsampled by a factor of 2, I'm not sure how that looks to you all. But here you can see this engine. When I was working on it, it ran at 4 milliseconds doing this scene. And then it, for some reason, suddenly got slow and went to 10 to 12 milliseconds, and I stopped working on it. And I've never been able to figure out why, and I've never fixed it. So I was kind of keeping secret what it was and how it worked so that I would have a little advantage, you know, of having a really fast engine that nobody else knew how to do. And, you know, I figured I'd publish at some point once I'd done something interesting with it. But now that I just don't have any motivation to do anything with it because it's so freaking slow. I mean, it's still 60 frames per second if I'm not using OBS, but I'm just not, I figure I might as well share it now. And if somebody else can figure out how to make it run at 4 milliseconds per frame on this GPU, you know, hooray, somebody will get it, even if it's not me. So here's what we're going to talk about. I have not organized this at all, so I don't actually have a plan or anything, but we're going to talk about how the raycasting engine works. We're going to talk about how the world is stored, because the other thing about this is that it's a very, very big world. It's, if I recall correctly, what's the twice 64,000, so 128,000, whatever the actual number of that is, you know, the power of 2. So 120,000 by 120,000 by, I'm not sure how tall the voxels are. That's a little weird. It's kind of a 2D engine, or the map is really 2D, so it's a little arbitrary. So we'll talk about how that map is stored, which is both how the voxels are stored in detail and how I packed that large a map into 4 gigabytes so that it never has to upload. So that was one of the things about a lot of the old voxel engines I worked on when I was trying to make really big maps. I would make infinite maps like Minecraft, and as you move around, they'd have to scroll. I didn't see the Handmade Seattle talk, so I don't know anything about it. Um, and uh, um, so yeah, the old engines, they would have to do the uploading, and that involved multi-threading to make that work well. And I was just like, let's sidestep all that. All this is running in a debug build in VC6, which is from 1997 or 8. So the code is not at all optimized, but all of the code that's important is running on the GPU, so the performance of the CPU code just doesn't matter. I mean, if I were releasing a game, I wouldn't do that. And in fact, this fork of the engine that I was working in when the performance died is notable because what I was actually working on was adding a compute shader that would update the map, so that in the CPU you could say, here are the things to change, make a little list, hand it off to the GPU, and the GPU compute shader would distribute that over all the different maps that need to be updated in a way that, so that you could kind of do it asynchronously on the CPU, then hand it to the GPU, and the GPU would do it synchronously to not break the rendering. And why was I talking about that? Oh yeah, so just because updating it from the CPU, you have to do all these little sparse updates. Uploads are terrible. So this engine is written in OpenGL. Not necessarily something you'd want to ship with, but not something I'm willing to rework just to see if I can get the performance back. And the flickering at the far end of the map is the lack of LOD. So this engine was all designed to be very, very good at doing LOD, but I never put the data in, the LOD data. So it's sparsely traversing. It's like stepping over 4 voxels at a time and things like that in the distance, and that causes all that stuff to flicker terribly. And I just ignore it because I know it's fixable. It's just never been the priority. And that's one of those things I would work on if the engine had not suddenly tanked and stopped running fast. So for anyone who doesn't know that story, even though I've said it many times on Twitter, and you're probably all here from Twitter, but you know, the people watching the archive are perhaps not. The story there is that I had this engine. I forked copies of it as I was making major changes. And on the most recent fork I was running, I was getting 4 milliseconds per frame on scenes like this. And then one day it was suddenly getting 10 to 11 milliseconds per frame on scenes like this. And I couldn't figure out anything that I changed. I tried to roll back. I went back before I forked it. I could not find anything that I changed on my machine that would explain that. So this is an older high-end GPU with a GTX 980 Ti. So I tried a different machine with a 1080. I don't remember if it's a 1080 Ti or not. And that one ran at about a similar speed, maybe a tiny bit faster. And again, the CPU doesn't matter. And then recently I tried it on a 3090, and it was like 8 or 9 milliseconds, I think. So faster than this, but faster than the 10 or 11 that this gets when I'm not in OES, but not even close to the original 4 milliseconds. So I don't know what I changed. I didn't think I had changed anything. All the evidence of trying to roll things back is that I didn't change anything, but maybe somehow I changed something and didn't check it in and skipped a version. I don't know. Like something happened and I can't figure it out. There was a big speed up that I had made that I remember the details of, and I've checked, and it's all fixed in the current versions, in all the versions that I've tried. So I don't know what that was. Yeah, it's kind of like a Berenstain Bears kind of thing almost. And as I noticed on Twitter, at this point I would think I was confused and it had never run at 4 milliseconds, except although I was kind of keeping it secret, I had for once actually recorded a video very soon before it tanked. And well, it wasn't very soon chronologically. It was a few months before, I guess, but very soon in terms of the development. Like I did that, and then it might have been actually very soon chronologically, but it was very few days of development between when I captured that video, which shows it running at 4 milliseconds. despite me capturing it even. Anyway, so I guess we should start talking about the thing. Yeah, it's not a driver. I doubt it's a Windows Update thing. As I said, I tried this on other machines, but of course those machines are running Windows 10 or 11 or whatever. But because this is Windows 7, there weren't any updates, although there could have been secret updates. But the odds of them doing a secret update that would do that, I did try different NVIDIA driver versions. Obviously, I hadn't changed it. Like it literally just changed on me, it seemed like. But I did try rolling back driver versions and newer driver versions and could not make any difference. Only ever got the current performance. So I don't want to relitigate this performance stuff. We talked about it for ages on Twitter, and the whole point of this stream is I'm abandoning any hope of ever fixing it. So that's why I'm talking about it. And if I thought I could fix it, I probably wouldn't want to talk about the engine yet. So don't try to fix it, because then I'll stop talking. So I'm sorry that you can't see it because of the contrast. Maybe I can figure out where that contrast thing is. Where would that be? Make ground or make voxels? Make ground is, oh yeah, here it is, right here. It's this line right here. It's the last thing I did probably. Yeah, but I don't, it's L0. I think L0 is the range of luminance. So if we make that like this, maybe it'll brighten the luminance. Of course, I've just been doing this for ages with the... that didn't make any difference. Are these being cached? I think they might be being cached. I don't know why, since there aren't that many, but... Make ground. Wait, this has its own... Wait, it sets these R values and doesn't do anything with it. Oh, because I forked this code. Right. Hey, look, I don't make them anymore. Let's see what this does. In before this fixes it. Nope, this didn't fix it. Plus these luminances aren't going up to 255, so I'm not even sure that's right. Make ground chunk. Whoops. Boy, when am I going to talk about the voxels? Let's see. This one is... Yeah, these are just ignored. Guess I forked this function, clearly. Well, I don't want to spend any time on this, so we'll just do some other hack. Let's see. We're calling make terrain tile. We're doing it here. L equals R range 0, 255. Let's just see if that makes any difference or if we're still not updating them. No, it's not. It is not doing it. Make terrain. Am I in the right? Can we see if that's being run? It's being run. L203. 165.80. Okay, all sorts of different values. Is it not actually uploading it then? Maybe I have to build terrain data? That could be. That could be. That would make sense why it didn't fix it. Okay, this is the last thing I'm trying, otherwise forget it. Yeah, all right, forget it. Let's see. So I apologize that this ground is... Oh, that's a bug. I say only part of a tree. I thought I had fixed that. That was part of why I was doing the GPU updating thing too, was to make that all consistent. But updating the map from the GPU. Okay, so let's start talking about this engine. All right. So how do you trace voxels? And so these are literal, like solid colored voxels. It does actually know exactly where it hits on the object, and so it could like do a texture lookup or whatever, but it's also not quite perfectly precise, as you can see with this little seam. I can't move slowly enough. Wait, can no, I can't move slowly enough. I don't have any ability to move slower than that. So, but you can see that despite the fact that I use kind of a height field for the ground, like, you know, we do arbitrary voxel stuff. Um, and wow, that bug is, oh, it's only on that tree though. So I must just have some bug in converting that tree to my format or something. Usually in the past when I had that bug, it was like a specific seam along the map that was always busted. Um, so, so how does this thing work? Okay. We're going to stop demoing it and start. No, the trees are actually, I bought the trees. And there's just some finite 30 of them or something. And maybe I do 4 rotations of them. I'm not even sure I do the rotations. So this is a raycast voxel engine. So the format is very similar to an old format called VoxLab that Ken Perlin, not Ken Perlin, Ken, the build guy, Ken Silverman, thank you, that Ken Silverman did after post build when he was just doing his own thing. So the format, you split the map into, you treat the map as 2 dimensions. So you have what I consider the X and the Y axes, and Z is vertical. So across this XY map, at every XY location, you have the list of all of the voxels for that column. And the way you store that list is as what I would call an opaque run length encoded format, which means that you say, if it's an opaque voxel, then it has a color, and if it has a if it's a transparent voxel, it has no color. So you encode with run lengths which ones are opaque and which ones are transparent, and then you also have the colors. Now, you know what a real opaque run length encoding, what I would normally do is I would store, you know, here's the length of the transparent things as a single number, and then I would say, you know, as a single number here, and then that was just meant to think. And then you would store the length of the opaque data, and then you would store the values of the opaque data. So, you know, maybe the opaque data is, the colors are 1, 3, 5, and 7. So that you know, looks like that. Why did my brush size change between those? Oh, because it's, does it actually store it? No, it didn't change. I just drew it that way and wasn't paying attention. So, you know, it's actually 1, 3, 5, and 7. So I use a similar format for this voxel stuff, but it's a little different. It stores, you can think of it as, it stores the, wait, why is this not, okay. It doesn't look black here, but I guess it looks black here. How do I, is it this and these are all colors? Is that how this works? Yeah, I guess so. So, so you store, now I'll be more explicit about the storing. You store the length of the transparency, and then you store the length of the opaque. Oh God, how does this work? And you store effectively a pointer. God, use a smaller brush, you store a pointer to the color data. All of this matters because you're running on the GPU and memory fetches are slow. So you want the real color is the triangle circle. Thank you. I mentioned the details of the data storage because it'll come back and matter. You don't actually have to know. It just matters that it's relative. But anyway, so you store. You don't actually have to know that for this stage, but you might as well get familiar. So you store that, and then you store another one, and you store another one, etc. And I'm trying to remember if it's null terminated or if it's got a length. I think it's got a length, a counted length, so that you don't have to fetch one and wait for that fetch to resolve to know that you're done. I think that's the logic. So that's the format that we're going to ray trace. We store this information for the vertical columns in the world, and we're raycasting horizontally. I need this to be on screen. And we're raycasting primarily horizontally because we're looking across the world. And you can look up and down. I think because I don't actually have like a wall, which you can build like a perfectly wall, and you can see that all these things resolve as exact squares, so you could put pixelated art on a wall. Anyway, so if I look straight up or down as much as I can, again, I'm sorry that the contrast here isn't higher, but you can see it all looks perspective correct, but you can also see at the very bottom there's some weird distortion you may be able to see. Is there a brighter spot? No, because none of this stuff is bright. I really wish I could fix that. Maybe I can do it here. Yeah, okay, so you can see there's an artifact here where I didn't quite do the math right to prevent you from looking down further than straight down. So if you look straight down, it goofs out. Because there's a hack. In fact, you can't even look perfectly straight down. You need to slightly limit how far you're looking down and how far you're looking up. But also, what I was trying to say is if I built like a big vertical wall that's very flat and like has a checkerboard on it and went up to it and looked down, it might currently show some warping. You can't tell that with trees and ground, and it's fixable. I just never got around to fixing it. So, oops. Can I open a new canvas? Can I open a layer and hide, or start a new layer and then hide this layer or something? I can start a new layer, but okay. So so here's the deal. We have an eye, and we're trying to raycast a scene that's made of vertical spans of voxels. And our eye can be looking down at them like this. But to start with, we're going to solve the case where the eye is not tilted down. It is flat. If we look at the map from above, so these columns of voxels look like this. We allow this camera to rotate to any angle, and we do solve that problem, but we don't solve, to start with, the vertical rotation, and we do not allow this kind of rotation at all. You could do it by rendering a slightly larger image, well, potentially a much larger image, and then just rotating that 2D image. And we already actually do a trick like that to get the vertical rotation. So it's not infeasible to add, but you probably don't want to allow it to rotate to 45 degrees because at at 45 degrees, the box that you'd have to, the bounding box would be pretty big, but you could do it. But that's one of the things where to get super high speed, we accept some compromises. All right, so how do we do this? I kind of like to undo what I did on this layer, but I can't. So I'll undo that. Okay. Oops. All right. So, because you're on a 2D map, what you can do, oh, I guess that means I wanted to. Oh well. I forgot I was going to explain this part. So what we're going to do, we want to figure out what to draw this particular pixel. Let's say I'm looking at the wrong layer. I'm drawing on the wrong layer. Yeah. So let's turn that layer back on. No, I don't need to undo anything. So, say we want to know what's at, like there's a virtual screen here, and we want to know what's at that pixel. So we want to do this. All right. What do we do? Well, we do the obvious thing, which is we divide this up into a grid. And I'm not going to fully dice this grid. And I should use a different color. Sorry. So we dice the map into a grid. And I'm not going to fully do it. And the idea is that this is one square of the grid, right? And we take this line and we step through it and we say which columns, right? Because we're looking down on columns. So we say which columns does this thing hit? And so it hits this column, then it hits this column. That's a terrible color. It hits this column, it hits this column, it hits this column, it hits this column, etc. And we say, okay, for each of these columns, we have two things. We actually have a ground, which is not using that run length encoded format. The ground is a height field plus a displacement that is just vertical. So they're cheated. And if we look at them, and again, I apologize for the terrible contrast. If we look somewhere where it's really steeply vertical, well, I don't know. Can you guys see that at all? Or is the contrast too low? We can see it. All right. Let's go to where there's a boundary between the grass and the tall grass. Okay, so here you can see that the ground, all of the voxels are the same color, right? It doesn't do that run length encoded thing. It's actually, there can't be a gap. The top of the ground, it extends down infinitely. So if I actually try to go into the ground, instead of the normal thing that you see in games where there's nothing underneath, these extend down infinitely, and that's how the raycaster sees them. So now there is a trick that I do in case you get vertical stuff. How do I go really fast? Is it Alt F? No. Shift? No, it's not even F. It's G. No, it's not G. It's Control G. No. Shoot. H. There's a key to let me fly really fast, but I can't remember what it is. Where's a place that's very vertical here? Maybe. Or I may have taken them all out on the current map. I don't know. Okay. Yeah, it's too dark to see. Oh, there, you can see that. So, yeah, you can't tell, but it actually changes the shade of the different voxels as it goes down. They get slightly darker, but you can't tell. But anyway, so this is a limitation of the engine, just that the ground doesn't actually have full coloration. It just has a color at the top. And you can also see it has a shadow per voxel. It has, is it in shadow or not? And it just goes all the way down to the ground. So that's true for the ground. The idea is that basically there's the ground layer and there's object layers. And if you want to do something like flowers that stick up from the ground, they can't use this ground thing, but they could kind of use the ground thing because they could use the ground thing where there's nothing underneath it, where there's no holes, where it's convex effective in some sense. So you could put only the parts that are not, that do not extend all the way down to the ground. Like you could put a flower stem that's vertical into the ground layer and have the flower itself be on the texture layer. But I haven't, the object layer, but I haven't done any of that stuff. I just like proved out the object layer with this stuff. Okay, anywho. So, right, we do the obvious thing. We step, we step, we step, we step, we step, we step. And each time we step, we look at the ground and we say, as this voxel traverses in 3D, I guess the thing to do is just to erase. I erased the wrong layer because so as the voxel is stepping along in 2D, in this view, that means it's stepping along like you can't see any depth here, right? So it's effectively stepping in a column and then in the next column and in the next column, you know, on the 3D map, and evaluating everything in that column against this ray, right? It's the obvious thing. And the map is, as I was saying, 128,000 by 128,000 voxels. It will step up to 3,000 times in the rendering. Each pixel potentially can step 3,000 times. And for LOD reasons, it starts skipping by more than one map square as it gets into the distance. So as it gets into the distance, it actually evaluates this voxel well. It steps like this and this. Conceptually, what it's actually going to do, wrong layer again, of course. Conceptually, what it's supposed to be doing is it's going to evaluate this LOD voxel and then this LOD voxel. But I haven't built that LOD voxel data, so actually what it's doing is it's evaluating that voxel and then this voxel and just skipping this voxel. And it keeps doubling its step size as it gets further and further into the distance. So even though it takes 3,000 steps, it's I don't actually know how many steps it's how far it's gone, but it's taking steps of, well, it should stop at 16, but it's taking steps of size 64 when it gets into the far distance. So it lets it go out like 30,000 voxels or something like that. And if that LOD stuff was actually hooked up, you can see this LOD plus equals 1. This is saying use the LOD model, which doesn't exist. This is all, don't worry about this. This is all cut and pasted because it didn't matter. But anywho, none of this explains how it's fast. I mean, the stepping in the distance obviously helps the performance, but stepping 3,000 voxel columns per ray, per pixel, and having to test against multiple things is not going to be fast. So there's definitely more to it. So first of all, the GPU is a SIMD sort of machine where you have 64 SIMD lanes or 32 SIMD lanes or 4 SIMD lanes. It's not defined. And each SIMD lane can be processing totally different stuff, but it's got to run through the code in lockstep. So it helps if it's all processing the same stuff. And what we can do, and it's a step towards this, is we can say, well, we'll make all the lanes step through the same voxel column at the same time. So they'll all load this voxel column and intersect against it, and they'll all load this voxel column and load against it, and this voxel column and this voxel column. And that means they're all testing against the same data, and that data becomes faster to load. Now, does that make sense? This is important. We're about to hit the actual secret of the engine here, so I need to make sure that part makes conceptual sense. That is a thing that would be happening in SIMD. So like on GCN, which is the older AMD design, we understand how that works. They've exposed a lot of the details, and so we understand that there are so-called VGPRs, vector general purpose registers, and SGPRs, scalar general purpose registers, and the scalars are shared across all of the SIMD lanes that are running at the same time. So that would mean that doing this stepping across the map, the registers involved in that would be scalar registers because they'd be shared between all of them, and the vector registers only need to get used for the vertical stuff. Because, so I guess I should have illustrated it, right? So the idea here is that we were stepping, oh, of course I'm drawing on the wrong line again. The idea was we had one pixel and we were stepping it and looking for intersections here. I never drew this out, right? And we just step a voxel at a time. And the idea now is we have a whole bunch and they're in the same column, and the way I'm drawing them, they're kind of equally spaced. That's not actually necessary if they're in vector registers. They could be spaced differently, but they're all in the same column, so the only thing they have to keep track of is the height. And when they intersect with this column, right, there's some run length spans. So there's empty, there's empty, well, let's actually just leave empty. So there's maybe some solid data here and some solid data here and some solid data here. So each one can say, well, do I overlap that? No. Do I overlap that? It's a little more complicated because it's actually treated as a little cube or stack of cubes. And when the ray enters, it maybe enters here and then hits here and then hits here in terms of where it hits on the grid. And so if this voxel is empty, but this voxel is solid, then this ray has to detect this intersection. But if this one's solid, it has to detect this intersection. So again, I'm sorry I used the same color for those. Right, so there are different possible intersection points. We don't care about it coming out the back. And so we actually have to test those. So the test against the column is a little more complicated because you have to test for coming in and going out. So the way that actually works is that we take one of these orange columns, which is saying at this stage, we don't know where it's solid and where it's opaque. And we take a ray that's coming in and we say, here's where it enters and here's where it leaves. Then we can keep track of that range. And we ask, does that range overlap any of the opaque runs in here? And if it overlaps an opaque run, like say there's an opaque run, say there's this opaque run, then we can say, okay, does it overlap when it enters? Because that means it hit a front face. And if the answer is no, then it absolutely hits a top face, assuming that this ray is going downward. So we don't know which top face until we go through and say where exactly does the opaque start and end. Maybe we have to do a divide to find it. And from that divide, we'll find this thing. Okay. But you can see that all of them are doing similar work. So this is actually not pushing the GPU hard enough, and this will not be very fast. The way we make it fast, what a mess. The way we make it fast is we take our view, and we take some pixels that we want to render. So in the old thing, the thing we were just describing, here's the screen that you're looking at. You know, oh, so how do I draw a monitor and make it look like a monitor? There you go. We were looking at a stack of pixels. We were saying, let's have the SIMD lanes, so a wave or a warp or whatever, a single unit of GPU work was going to take a stack of pixels and trace a stack of rays. And it turns out that if you do that, those rays, and you march those rays through columns of the map in the way we were saying, then those always stay equally spaced because they started equally spaced in the pixel space. So they were all that whole warp or whatever you want to call it was here, right? And it was stepping through the map like this. In the new scheme, we're not going to take a stack of vertical pixels. We're going to take a stack of horizontal pixels. So there's like 32, or I think my wave front is actually 64. I use 64 SIMD units in a job or whatever. So they're going to go like this. And these are going to use vGPRs in the GCN AMD platform. And this can be rotated, right? We said the map can be rotated. So this whole thing could be rotated, and these are not stepping in a simple way across the map. But it doesn't matter. When you have a line going across the map, the math to make sure that your things go like this. Again, sorry for using the same color. Oops, missed. Wow, terrible. The math to figure out which things it lands in, or actually is, if you remember what we were talking about, it's where there's an intersection. So there's an intersection here, there's an intersection maybe here and here and here. And finding all of those intersections is actually straightforward, but we have to do it independently for every lane. However, the fun part is that this thing, these vertical stacks, we do still do them, but each SIMD lane keeps track of 32 vertically spaced rays. So this stack is now all being tracked in one SIMD lane, and it stores a bit field, a U32 that says which of these are active, and it says what's the slope what's the direction, the vertical direction at the bottom, and what's the vertical direction at the top. And they can figure out the vertical direction for any of the ones in between by interpolating. It actually pre-computes that. It stores the bottom and the step size, or the top and the step size, I don't remember, so that it can do that. And then step size keeps spreading as it advances. And the math to do that is all very straightforward. So what does it actually do? We take a step, and in the code, when we take a step, we enter a new voxel, we're going to say this area covering this stack of voxels, how does it interact with the run lengths in that column? And if the bottom of it is up here, it doesn't interact with this at all. And if the bottom is here, it does interact. And we can like linearly traverse it and say, let's look at this voxel, let's look at this voxel, let's look at this voxel, let's look at this, not voxel, look at this pixel ray, this ray, this ray, this ray. Eventually the rays go off the top and we're not overlapping that anymore, and it can early out. You could actually say, oh, I can do math and figure out it's exactly this set of them that overlap. But we actually have to do some processing for each one anyway. We have to store away some data for each one because a single SIMD lane cannot keep track of 32 voxels worth of information. Remember, we're going to early out. We're going to say we hit 32 pixels of information. We're going to hit a voxel and we need to store, okay, we hit this voxel. We're going front to back. So we hit a voxel, we're done, but we're still tracing all the other rays. So we have to store some info about what voxel we hit so that we can color it correctly. We could immediately do that work, or we can store that info. And the point is we can't store it in registers because we would need 32 sets of registers with that information. So we either immediately compute it and store it, which requires us to iterate through each one individually, or we store some information about all of them. And again, it just makes more sense to iterate through them. We're only going to iterate through them once because we only do this once when they hit an object. So what we end up doing is we end up taking a patch of the screen. Let's see, which layer did I have? That one. Right, so what we end up doing is we end up taking a patch of the screen, and this way, whoops, did it again. This way is SIMD lanes, and this way is bits that a single SIMD lane is keeping track of. So each SIMD lane gets a 32-bit number, which rays are still active, which rays it hasn't processed, and a float for the bottom or the top, I forget, and a float for the step size between them, and then actually more floats for how to advance them. And because each one is in a separate line, there's also some vectors for how to move on the map. All the map movement in X and Y is done with integer fixed point math. That's just so it's all precise, doesn't round differently. You don't have precision problems with being closer to 0 and not closer to 0. And all the vertical stuff, because the scale is much smaller on the vertical, I don't allow you to go super high. I think the cap is 32,000 or so, but I don't think I ever even want to go that high. The vertical stuff is stored not with fixed point, but with floating point. So the idea is every little job that, if you were doing a pixel shader, right, each of those jobs would do 64 pixels. And here they're doing 64 times 32 pixels. And the step math sorry, it's such a mess. This step math is able to process all 32 at a time very efficiently most of the time. There's a bunch of optimizations for that. So at all times, the SIMD lane knows, so here's, let's use red again. So here's the stack of rays that it's tracing. And, maybe it's a little sparse because some of them have hit. At all times, it knows effectively the top and the bottom of it. So it's very easy to cull quickly against, say, the ground. It can say, oh, no, all of these are above the ground. We don't have to do any ground processing. And it's very easy for when looking at the rest of the other data, like the run length encoded data, to say, oh, the entire thing is above or below these runs, and cull out very quickly. And then if it does overlap, usually it can, I don't know if I do that correctly, but it can iterate from the correct end and peel off the rays that actually collided and not do any extra work for the other rays. Once they're sparse, that peeling off may seem a little tricky. Like if you want to loop over from 0 to 31 and some of them are sparse, then you'll be hitting these rays that are, you'll be stepping over the rays that are sparse. But in fact, let's find a place where we do that. Process span. What we do is this. We use some stuff that you're guaranteed to have that's fast on the GPU, which finds the set bits. And then, so we find the first set bit, we iterate over all the bits, we clear the bit that we just looked at, and find the next set bit. And that way we only step over the active rays. We don't have to process the non-active rays. So it can do this stuff relatively efficiently. And there's some more stuff that I'll talk about when I talk about how the data is stored in detail. But for now, I want to just stick to nailing down the rendering. I think I've said the main issues in the rendering. So if there are questions, if anything's not clear, please go ahead and ask. Because like I said, I'm just winging this. I have never tried to explain this to anyone in detail before, and I'm just making it up as I go. So like, I apologize for reiterating things or not explaining things, and for the terrible art. So let me see if I can find render voxels. Where do we actually draw? Here. Yeah, that's the ground shadows. Okay. Here it is. So I'm currently rendering 1600 by 1600 rays or voxel or pixels. Displaying, I'm not sure what my display resolution is, a little smaller, and I resample it here, resample program. I resample it, and we'll talk about that a little bit more because we still have to talk about how tilting the camera works. Where did you read about the specific scale registers being shared? GPUs still seem somewhat untouchable to me just due to lack of resources. So GCN is the AMD architecture that they documented the assembly language that the GPUs actually run under the hood. And so there's a bunch of documentation about that. AMD GCN. I don't see any links on AMD, but I see third parties with it. Maybe the Wikipedia page will have the link to the AMD page. Well, yeah, I'll just give you this instruction set. So that Wikipedia link is to the sub portion that has links to AMD's documentation. Now, getting through that documentation might be pretty hard if, because it's got all sorts of detailed stuff and you have to understand stuff. So you should probably look for some PowerPoint presentations or something like that, which probably AMD did back in the day. This is all pretty old now. Yeah, like that one, the first one on that page is 2012. Oh, they've documented Vega. Okay. It's just 2020. So, and of course that's not on screen for people looking at the archive. So let me at least let them see it. But yeah, there's just, there's a lot of this. There's like just getting an inkling of what's going on in terms of warps and all that nonsense. There was a good presentation, I think it was SIGGRAPH, or maybe it was a special GPU conference, that somebody walked through AMD, NVIDIA, and Intel and explained all their terminology sort of in terms of a baseline. But even his terminology, I think I'm not 100% thrilled with. I prefer to just think about SIMD lanes as like sort of a clearest terminology because that's our GPU terminology. And they really are just SIMD lanes. So let's see. What else did I have I not explained? Anyway, so the performance, the big performance difference here is the fact that you process these 32 rays at a time, which you can only, if you had to store 32 different heights and different steps and all that stuff, you couldn't fit that in a single SIMD lane and not run out of registers. But because they're all evenly spaced, because our rendering is flat, or we're not tilting the camera, that causes them to all be equal. There's no perspective tilt, so they can all stay in the same column and be evenly spaced apart, and they stay evenly spaced apart, so you can just, you only need a few registers to explain that. That's how this thing manages to have a small enough data to be able to do 32 rays per lane, and the format of using the run length encoding allows it to quickly call against all of those rays at once against things. And if the ray collides, that only ever happens once to the ray, so it can be efficient. Now it's a little tricky. Once it's sparse, it may look like it collides, but only the sparse ones collide, so the performance isn't quite the gain that I was talking about. Right, I mean, I said it. I don't know how else to say the same thing. But by doing that, I've turned, instead of dividing by 64, I get to divide by 64 and 32. So the 1600 by 1600 thing only requires if you imagined it was a pixel shader, so we don't get to divide by the 32, but we do get to divide by, right, so, yeah, I mean, it's just that. Is that right? 1600 times 1600. No, I did. Yeah, okay. So we're doing that many pixels, but we really only do that much processing, right? And it's like, that's such a huge difference that it can let you do things like be 4 milliseconds doing this gigantic scene with 3,000 steps across the map. A lot of the God, I don't know what I was going to say. I guess I need to hear what I said, the last 15 words I said, so I know where I was going. Because I stopped to read a chat message. 80,000. Oh, well, I don't know. If nobody in chat is going to tell me what I said, then we'll just move on. Okay. So, so we have our screen. Oh, here's a fun thing. So the original design that I had, instead of this having the 64 CMD lanes do this, it's a 64 by 32 rectangle, but let's just call it a square. Instead of having it do a square, I was originally going to have it do one giant column. It would do 64 times 32, which is a 2,000 tall column, which is way oversampled, and then I would have to resample it at the end. And the idea there was that that would let it, on a GCN-like architecture, take, when it took steps in the map, every single ray being processed would all be in the same tile on the map, and it could actually do that thing of using the scalar general purpose registers and reduce the vector general purpose register pressure. But it turned out to be a bad idea, because one of the things you really want in your GPU is, I'm trying to remember what the word is, occupancy. I can't remember the word for it, but so the point is, when a ray dies, we're no longer active. Like, okay, if every lane is doing a ray, just one ray, when a ray ends, when we hit something for that ray, we're no longer doing useful work with that lane. that lane is just turned off and not doing any useful work. But we keep running the shader. We keep running as that column steps into the distance, as that stack of rays steps into the distance, until one of the rays finally, or horizontal stack of rays, until all of the rays end, and then that shader can stop running once all of them have stopped. So what you want is to pick a set of rays that are packed together and are likely to stop at a similar time. So if you pick a little square on the screen, that's a giant square for us, but 1600 divided by 32, there's a lot of little squares actually. So if you pick a little rectangle, then if some of them hit the ground, probably all of them are going to hit the ground. Some of them won't. Some of them will keep going. Like once in a while, you'll have a set where some of them hit early, but the whole thing just keeps going. And if I run it, oops, don't need to bring it up. If I run it and we look at it, and you have to imagine pixels, so they're pretty small. You can see at the middle, we trace all the way into the distance. We're using all 3,000 of those steps. But at the bottom of the screen, we're not using that many steps before we hit the ground. In fact, if you look at the time, it's 24. And if I look at the ground, it goes down to 17 because all the rays are stopping sooner. If I get really close to the ground, because I'm recording, there's a bound on how slow it can get, or how fast it can get. But yeah, it's under 10. And yeah, when I'm not OBSing, like that can be 1 millisecond or whatever. And if I look up, well, there's actually an invisible sky that stops the rays from running forever. But the rays that trace to the horizon line, where you can see the horizon, all those rays are stepping many times and taking a long time to run. But all the other rays closer aren't doing that. But we're batching them up in these batches on the GPU. So any of these that basically overlap the horizon will run 3,000 steps. So, the horizon is kind of flat. So generally only the middle jobs do it. And again, it's 1600 over 64 by 1600 over, so, that's 25 by 50. So, which one's vertical? 50 is vertical. So, it's maybe 25, 50, 75 are going all the way to the distance. The ones in the middle are going all the way to the distance. And the ones near the bottom are ending earlier. When I tried the thing of doing the SGPR, so I made all of the rays for the job in one big column. So, 64 SIMD lanes, each doing 32 things, all stacked in one big column doing 2,000 things. Every single ray job would go all the way to the horizon because the middle rays would all make it to the horizon. And so every single job would run the full 3,000, and it was actually very slow. So it was actually important to split this into these rectangle shapes so that most rectangles can stop earlier and not go all the way to the horizon. Again, this is like geared at being a first-person outdoor giant world kind of engine, and that's a perfectly fine trade-off in my opinion. Obviously, if you could set up a world, like if you fly, if you're very high in the air, then all of the rays can take a while. And if you didn't have that sky ceiling that caps the rays and causes them to terminate early, it would not be as fast. So you have to make some compromises to get this speed, and I'm okay with that. So that is why it was a bad idea to stack them all vertically. Okay, so like we said, there's 25, there's 25 columns, which we're going to draw as 6 or whatever, and there's 50 rows. So this is the whole screen. Wow, those are terrible. And each of these then is this little 64 rays by 32 rays. Yeah, there's no, I meant to mention this. There's no acceleration structure. There's no speed up for empty space. That's a really common thing in ray tracing things is you say, oh, we've got this big area of empty space. Let's have some way to cross that with very little computation. Instead, this engine relies on the fact that it's only got to trace 80,000 packets, right? We'll start using the official terminology. Each lane traces 32 rays, which are a packet. And those 80,000 packets, because it's a GPU and it gets to do 64 of them in parallel, it can do them very fast. And we have some tricks to step through each grid square efficiently if there's nothing to do because it's empty space. But we don't have anything to step it more than one tile at a time because there's empty space. As I mentioned earlier, for LOD reasons, we do start stepping multiple steps at a time in the distance. You don't have to do that, but as soon as you get to the point where your rays are smaller than a pixel, you might as well LOD because you're not going to resolve the details anyway. And then once you've LOD'd the data into larger chunks, there's not that much point in stepping in the finer chunks. Like if you literally LOD into voxels that are twice as large, as you've seen, the engine resolves the exact positions of those voxels. My plan was actually to do the voxels where you LOD along the X and Y on the map 2 by 2, but the vertical axis you don't bother quantizing down, or you don't at first, and then maybe you do later. And that lets you capture like terrain variation better because you still get more continuous heights, even though the voxels are now half sized. But because they're in the distance, hopefully people can't see it, but aren't aware of that being odd because you're doing LOD already. So if people are thinking about the individual pixels of the LOD. Anyway, all right, so here's what we're doing. We're stepping all of these, right? And these are going up in the air and these are going down in the air. And again, this is standing in for a big grid of stuff, but this is all one job. So one thing that we do is we actually have two shaders. And if the rays are going up through the world, we use one shader. And if the rays are going down through the world, we use a different shader. And that means that when we have to do, nope, this one. That means when we have to do this comparison and this overlap, here, this one, where I said, remember, like, oh, I need to detect that it's the front or the bottom of the voxel that I'm intersecting. Well, that's because the ray is going up. If the ray is going up, it can't hit the top of a voxel. But if the ray is going down, it can hit the top of a voxel and can't hit the bottom of a voxel. So the math is different for those. And the easiest thing I could find to do it was to just have two separate shaders. And in fact, what we do, because you can tilt the camera, maybe the boundary between those is here. So all of these are going up and all of these are going down. Let's do this. This is easier for my brain. All of these are going up and all of these are going down. So to do that, I just issue the entire thing upward, and then this block determines which rays within each block. Every block says which are the. Sorry, I dispatch all of these to the up, to the drawing the rays going up, and it checks are the rays in this block actually going up, and if they're not actually going up, it early outs and just immediately exits for these ones below. And for these in the middle, it sets the initial list of rays only to that, and it doesn't do these rays, but it still has to do all of the work, right? Because it's the SIMD lanes are these and the bit field is the vertical, so it's only setting some of the bits and doing all of the work. But that doesn't matter. Like if you factored it the other way, it wouldn't be any better because the whole thing about the occupancy, that was what I was talking about at one point and never finished. The whole point about the occupancy is that as long as any lane is doing any work you still have to keep going with all of the lanes doing, you're using up the opportunity to be doing more work. So we bite that bullet, you know, we'll end up drawing these and these in two separate shaders, but that's fine. Like, again, that only affects one row of the things. So 25 out of whatever it is, 25 times 50. Wait, I've lost something in the math somewhere. That's only 12. That's 12,000. I thought that 8,000. Anyhow, but you know, that's like 25 extra jobs or something. It's not a big deal. Well, the LOD world chunks are just LOD. You could turn off the LOD. I was starting to say that you could turn off the LOD and it would still be a fast engine. It just wouldn't have as far of a view distance. So as long as you're doing LOD anyway, then we start skipping the traversal. I was trying to say this. Once the, let's go back to the picture of that. So here we have the big things. We could keep stepping in the fine steps, but this step and this step are going to return the same data. Well, in fact, because we use entry and exit points, you compute. This is what we actually compute right now. Well, this is weird because it's the starting thing. I shouldn't have put it right on, I think. But so here's the, where didn't I have a color for this? Let's use red. You know, so you have the entry and exit, then the entry and exit for this one. And I didn't draw this one. There's an entry and exit in this area that I should have done. And then an entry and exit here and an entry and exit here. But we switched, because we're going to draw, instead of drawing this as its own voxel, we're going to do LOD and have a bigger voxel. Wrong color. I'm going to have a big voxel here. To draw it correctly, we might as well take a bigger step and do that. Actually, I do that. It's just I use this data. Well, there's no reason to take the fine steps. So when we start taking bigger steps, because we are exactly resolving all the cubes anyway, we're drawing the exact same thing we would have. So it's not an empty space skipping. It's just saying, let's push out the distance that we can draw since we're doing LOD anyway. Okay. What was I doing? Okay, so one of the details here is that we just have two shaders. And so you can see that in this code, positive, positive Z. I mean, I see a Z positive here, but where's the if def? Am I in the wrong shader? Oh, yeah, I'm not in the shader. That would be why. Yeah, we talked about the sparkles. That's from the lack of LOD. So you can see here, if the ray is going upward, so its Z value is positive, then we check if we're colliding from below. But for the other shader, we know that the ray is going downward, so we're checking if we're hitting the top, right? So there's that little bit of detail. Now, the question becomes, how do we tilt the camera? So here's that same thing we were just looking at from the side. So instead of it's our screen, it's our virtual window into the world, right? Let's not quite connect. That's a bad tangent. Let's draw that differently. That's a misleading tangent. Okay. So we have a camera looking through this virtual window out into the world, casting rays. Okay. And our engine only works when the rays that correspond to the pixels are spaced perfectly in the world, all in the same column. So I talked about this on that first slide. If I try to tilt the camera and do this, then when it hits these pixels, it's got perspective applied. And so the spacing of them, is that actually true? Is the spacing going to spread? I believe the spacing is going to spread. And so this trick won't work. I mean, you have to, the whole point is they don't spread if you slice it this way. Then they just do the same thing. Wow, that's a terrible correspondence. Let's do that. Okay. If you look at it perpendicular, then they take the same spacing in the same way. But if you look at the columns in the world, the perspective causes them to change their spacing, and it's not consistent, and you can't use that trick. So the only way to use the trick is to keep the camera level. So we keep the camera level, the raycasting camera. We just don't do that. But we can use, fun fact, reprojection. Reprojection says if you draw something from a particular point of view, then instead of drawing the thing, like so say there's an object out here, and it hits here. So we draw this object onto our virtual scene, but we also capture the first virtual scene onto a texture, and now we draw that texture in the world. Well, look at how the rays work. It's in the right spot. Obviously, it looks correct. Fun fact, if we build this texture with this camera looking flat, which I didn't actually draw it looking flat, so I guess I should redraw it looking flat. So the camera's down here, but looking flat. If we draw that camera looking flat, and we draw a camera from up here, and instead of trying to draw the scene, we draw the texture on this plane, it's not going to look right. We're going to say, oh, that's a plane that we're looking at from above. But if we put the camera in the same spot and tilt it, right, the ray still lines up with where the object is. And so we draw that object in the right spot, but we're only drawing some of what we can see, right? This plane, I used the same color for the plane. Right, this plane fit the old camera and does not fit the new camera. But the stuff that's in it will match. Now it will get resampled. We'll draw it once. We'll draw it originally, then we'll put it in a texture and we'll draw from it again, and that can lead to sampling artifacts that you can see, you know, the pixels don't quite line up the same way that they would originally. That's what we're doing, and we don't care. It seems to work fine. Again, as I said, if I drew an actual flat wall with like a checkerboard, it might distort because of something I never bothered fixing. All right, but what do we do about this vertical problem? Well, God, I'm so bad at using these tools. I'm so sorry. If we say we're going to have this other camera, let me just set the brush thinner. We're going to have this other camera that's tilted down, and so it's going to see this. Well, all the work we do on this camera, on this part of this texture, is wasted. But what we can do is we can use this camera, but draw a texture like this, even though I'm not looking down. Because remember, we're casting rays to draw this. I mean, you can do this in regular stuff. So we just don't cast these rays. We cast these rays, and we cast all the way down, even though the math is now very steep. It still all works. Like the spacing of these is still even when we're drawing them down if we choose these virtual pixels to line things up. So, however, there is a problem if we look at it from first person point of view. All right, I'm looking flat, and here's the thing I would draw. Now I look down, and I want to draw a thing. So we tilt the camera, and as we tilt the camera, this thing rotates up and becomes, say this. Let me use a different color. Let's use that one. Becomes this. Right, because we've rotated and that causes perspective. So this will get filled out without any extra perspective. And then when we sample it from the tilted camera, we'll get this extra perspective, which is the correct thing to happen to make the math all work. But the thing that you can start to see happening is, well, how do we draw these pixels? We said we're going to extend this camera down, this texture down, and cut this one off, right? We won't bother drawing those rays. We'll do this. But you see, I'm not capturing these edges here, right? The perspective tilt on that thing means I'm not doing it. So what we actually have to do is make the texture that we're drawing to a bit wider, well, in perspective too. So maybe like this. But now we got to draw some extra rays, right? That's an extra some number of rays. I should have used a more different color. Sorry. I was thinking, oh, these are similar things. I can use a similar color. And now suppose we tilt more extremely. We're looking down. So here's a side view. There's an object, or actually that could be the camera, the window plane. And we're looking down almost vertical, because we allow that. So we're looking like that. Okay, if we're looking like that, what does this look like in perspective? The texture that we're drawing onto, the bottom is very far away, and the tilt is very extreme. So this is what we need to draw, except this has to be wide enough for, right, so this is what we need to draw. We're going to draw raycast onto a virtual texture or a texture, and we're going to draw sample from that texture, and we need that texture to be wide enough down here to be 1600 or 1200 pixels wide, whatever our rendering is. Yeah, it's not square, sorry, or it's not, the rectangle shape here is correct, but you get the idea. This should have been wider, or flatter or whatever. But the point is that we're going to waste a lot of ray tracing work here and here. Another way to think of that is if we look at it from the perspective of the flat camera, right? The flat camera, I think this is normally how I think about it, so we'll see if this is any clearer, which it may not be. When you think about it from the perspective of the flat camera is going to draw some part of this texture, whatever is actually needed. And then we have the tilted. Let's move the whole thing closer. Is there cut and paste in this? I have no idea. Probably not. There's move canvas, but yeah, no. Okay. So we have our camera, and then we have our second camera that's tilted down. And so it's looking maybe like that. Let's say. Let's make sure it fits on the screen, actually. So we trace down to there and like that. All right. From this guy's perspective, he has to draw this much. He has to draw this much. And he draws it with stacks of pixels that are like this. Right, nice and linear. So what does this look like from his perspective if we're looking forward? What this looks like is he has this virtual texture to draw, and Red is asking him to draw, let's see, this is very far away, so it's shrunk. And this is closer, so it's taller. Okay, so normally Black would draw like this if he were flat. And instead he has to draw this. And this density has to be high enough to sample extra things. So you have to expand the density. Okay. So this is what it looks like from the perspective of the rays that you're drawing, which is what we actually care about. And that's why I wanted to switch. I realized that other one was kind of a rat hole. So we need to draw this. But if we draw it as a rectangle, we're going to draw all these extras. And you can imagine that as you tilt steeper, this gets even more and more wastage. But if you remember what we're doing on this, if you remember what we're doing, this is how we're drawing it. We're drawing these little jobs that are these little rectangles. So on this screen, if we make those little jobs that are those little rectangles, what we were doing is we were then dicing these vertically with a grid. But we don't have to do that. We can say this strip, we want to render from here to here with this spacing. Let's say there's 6 on every one. And this one gets 6. I apologize that that's only 5. And then this one gets 6, etc. So we ray trace this data, and we ray trace the same number of rays on every strip, but we change the spacing on each strip to reflect the spacing that the perspective projection needs. And that's 7 instead of 6. But anyhow, and we don't bother rendering these. And that's, just it fell out of how the thing happened to work, that we were rendering what are effectively strips. So the way this works in the engine is that, let's see, it was in that file we were looking at. You can see some of the work being done here, but does set uniforms do it? Or is it just done in math? It might just be done in math. I guess it's just done in math. So probably at the top of this, we're at the top of main. Compute sheared Fustum rays. That's the thing. So yeah, it takes the rays at the corner of the thing, computes the stuff, but then does some extra weird math to compute an expansion factor to determine how far apart the rays should be. View yaw. Oh, that's a matrix, right? So it does that in sort of a flat 2D and then rotates the camera across the map, the map direction. So doing this, you still need, okay, so it does this, renders all these strips, then it resamples here. The resample program is also a compute shader because I guess it could be a pixel shader, but then this compute shader says, okay, for this real camera, real position, where should this be on the thing? However, it doesn't actually do that correctly, and that's where there will actually be some perspective warping. I believe it just linearly interpolates a lot of stuff within a strip, and so it doesn't fix up the vertical spacing, because down here the perspective should cause it to sample very different pixels, like the pixel spacing should change, and I don't think it does that correctly. But it's also on such a small area, it's 32 pixels, that it may not matter. Like the old Quake engine only perspective corrected its texture sampling every 16 pixels, even running 320 by 200. So at this resolution, maybe it's not that bad. I don't know. Like I said, I have to actually put up a wall. For this data, for ground data, you can't tell. But for this terrain, for this clunky terrain. Anywho, so that's how we do uh, pitch. And as I said, I don't do banking the camera, rotating it. Where's my hand? There. So I don't do this. You could do it by applying a final, rotation like that. And that would involve wasting a lot of work on the edges, but you could try to do this same culling to only do it where you need it. I just like, screw it. I'll draw it a little bit bigger and let you wobble the camera a little bit, but I'm not going to let you fly a plane that tilts upside down. I also can't look straight down or pass straight down. You're limited to looking down just short of straight down, as I demoed. That showed the artifacts when you look almost straight down. And again, like, you could try to fix that. I have an old version of a shader that's not quite up to date. So this is the compute column shader because each lane computes a column. Compute ray shader, each lane computes a single ray. And so you could just cast rays straight down. It's no problem. And you could, this is what I originally thought you do, is you sort of draw a cube, like a cube map around the viewer, and you draw each face of the cube using this stuff. And for the downward face, you would use that ray shader. But it turned out that no, you can use this stuff fine. So like, one thing to think about how this stuff works, this one. Nope, this one. One thing to think about how this works is when you're looking really steeply down, so you have a ray that's stepping like this. What you're actually doing is you're evaluating the ray over these regions in each thing. And because we're doing run length, so this is a single ray, not even a ray packet, right? And so the thing is, this single ray eventually overlaps a run length, and we just resolve it correctly. Like, we do this, did you hit the front or did you hit the bottom of a thing? And that causes you to exactly resolve what that pixel should look like correctly with it being a cube. Even if you're looking really steep down, it just works correctly. So that's a nice thing about this that I didn't realize was going to happen until I implemented it. And then I was like, oh, that just works. So that's everything I can think of about the rendering. And then we can talk about the data storage. But let's see if anybody has any questions or comments or whatever. I guess I've already been going for an hour and a half. So. Yeah, well, I thought it was pretty fucking awesome when it ran at 4 milliseconds per frame. Also, this may be how VoxLab worked. That was a CPU engine that Ken Silverman made that used a very similar run length kind of construction. But it had artifacts that didn't resolve the edges of cubes exactly. So I assume it worked in a different way, but I don't actually know. Yeah, I can just run the live demo. The flickering is because there's LOD support, but no LOD data, so it doesn't draw the LODs correctly. So don't worry about the flickering. And there's an artifact that I've tried to put at the center of the screen at the moment where the ray stepping somehow misses everything and goes to infinity. And that was just a bug that came up at some point. Like I had stomped out all those bugs and fixed all those bugs, and there weren't any bugs like that at one point, and then they creeped back in, and I just never bothered fixing it. I was always like, hey, I could fix it if I need to, but let's not make that the priority. You can see the shadows here. Sometimes it decides that some of the ground tiles are in shadow, even though they should be. I don't know why, but whatever. Is this the 360 no load thing? No, it's not. I've made many voxel engines over the years. The 360 voxel no load demo was actually a demo where it had to construct the voxels on the fly as you moved around, but it just showed that when you turned 360, everything was loaded. But actually, most voxel engines keep everything loaded 360. It was a slight mockery of a version of Minecraft. Like for a while, there was a version of Minecraft that when you turned, you could see stuff load, but that's no longer true. And that engine was sort of a more classical block engine, whereas this one is a GPU raycasted engine. And then these are drawn with polygons, by the way. These are, and you can see I cheated the head to make it a little more detailed. Oh, in fact, yeah, you can see that the main voxels are twice as big as the world voxels, and that's because I mentioned at the beginning of the stream I changed the voxel scale to make the trees fit better. And because of that, these guys are at half the resolution that they could be. And so actually now I think that means the head is maybe at the same resolution. I'm not sure. Oh, okay, there we go. See if we can find somebody. Is there a guy with his head near a tree? Nope, I can't find one. No, his face voxels are still smaller than the world voxels. Anywho, what's the inspiration for this project? Just research or some other motivation? Yeah, I mean, I've always done rendering research since the 90s, so yeah, this was just another attempt. Hey, so the inspiration for this engine was I was like, we'll talk about this in the data, how the data works, but the core thing was I was like, one of the problems I saw in OBBG was that some distant stuff seemed to be showing gaps of some kind. I couldn't really make sense of it, and I wasn't sure if it was like a weird shader artifact. And it was only when they were really far away. And I decided I wanted to make an engine where I could do LOD correctly, quote unquote correctly. And by correctly, what I mean is that, like, if there's a doorway in a building with an open door, then the doorway shouldn't disappear when you get far away. And if there's a billboard that's very thin, the billboard shouldn't disappear. And this is all doable, but I wanted to think about a way to do that felt more user controlled, not, oh, find the right algorithm that magically makes all those things work. And there are other kinds of voxel engines that don't have that problem, that can allow thin objects within the voxels and stuff, but this kind of block thing where the voxel is entirely solid or entirely empty is not. Oh, so yeah, let's talk, before we talk about data, let's talk about the shadows. So the shadows are just a total hack. It's effectively like a light map from the Quake era games, with 1 pixel per ground pixel per voxel column. And it doesn't actually store light maps. It's a shadow map that stores a 1-bit shadow value for each ground voxel, for each column, of whether the ground is in shadow or not. And it applies to the whole column of ground. So when we were looking at that over here, the entire column goes in shadow or out of shadow at the same time, which is okay in the sense of, sure, like, why not have the whole thing in shadow or not in shadow? That's consistent with the light, like one's shadow shouldn't be, but is actually a little weird when you have like tree shadows, which can be disconnected from the ground and so can cast sort of sparse shadows. And here the ground is flat, so it doesn't matter. But if you look at a tree shadow, if you got a tree shadow against a steep thing, it won't actually look right. But I don't know if there are any. Like this. Yeah, like that doesn't have any sparsity to it, and it probably should. But yeah, you know, whatever. You take it. So that means there is a quote-unquote texture map that is 64,000 by 64,000 pixels, but it's only 1 bit for each one. And it's not actually stored that way. It's stored as an 8-bit or 32-bit value, and we look at that, and we actually it actually LODs. So once you start stepping 2 voxels at a time, that would half the shadows would disappear. So instead, once you start stepping 2 voxels at a time, it samples all 4 ground shadows. I don't know where that's happening. Somewhere on screen that's happening, but etc. I don't have any plans to make physics work on this. This is definitely intended to be primarily static geometry, not geometry that's detailed animations or whatever. I actually had planned to do a sort of Factorio game with it, and I had a whole bunch of ways to do the animation for that with that's all not physical though. It's all pre-scripted, so you just have canned animations programmed into the voxels. Let's see. Any other questions? How are voxels stored in an engine like that? Is there LOD? Okay, well, let's move on then. What were you doing in your early 20s? My early 20s, I was in college. I didn't graduate college till I was 25. Then I worked at a printer software company for a couple of years. And then I worked in the 90s at a game company called Looking Glass. It went through several names, called Looking Glass, and we made a game called Thief, the Dark Project, and I was the person who did the rendering engine for Thief, the Dark Project, which was also used for System Shock 2. Did the world rendering, not the character rendering. Yeah, as I mentioned, the performance here of the CPU code doesn't matter, so the fact that I'm using VC6 is not an issue. This is actually debug build, and none of this is CPU bound, so it's irrelevant. It does affect like load time some, but I've streamlined that as much as possible. So that's a giant 64,000 by 64,000 shadow. The actual map is 120,000 by 120,000 voxels, but it's split into sort of 2 regions. The center region, which is 65,000 by 65,000, and then the rest, the full 128,000 by 128,000 map, is meant to be stuff you can see, but not stuff you can travel to. So you're supposed to be game-wise limited to the 64,000 by 64,000 region. And so I only have the detailed shadows in that center region, and the shadows outside that region are going to be coarser. So this is probably 3.3. I mean, it's all extensions too, so it doesn't really matter. But 4.3, I mean, not 3.3. Yeah, because it's compute shaders, so you have to have a pretty advanced version. The way the ground shadows work to get that 64,000 by 64,000 shadow is it's ray traces, compute shadow cast, right? Just similar to the other thing that we were talking about, uses much of the same logic, but the rays, instead of spreading out from the camera, are all parallel, pointing up towards the sun. And it's a little more complicated to make that work because they can't start from the sun and come out because it's not a light source. So they start from the ground and go up. And it's a little bit weird how I make that work. But it basically is the same, and then does the same traverse the. Does it have the same extinguish? Yeah, it has the same thing we talked about where it steps through the set bits of the active rays that the thing is doing. So it does a similar thing with a little packet of 64 by 32 rays. I'm not going to look at stuff that's not this engine voxel related right now. But there is in fact somewhere an stbvm.h that's unfinished. That will never be finished. Okay, so the ground shadow thing is a total cheat because it's for a fixed sun location, right? I just wanted to look okay. But if you actually wanted to make a real game with it, maybe that wouldn't be good enough. You need objects to cast shadows. Like, that's a whole mess. So let's talk about storage. So I talked at the beginning about the conceptual storage, which is this run length encoding. And for this particular engine, you could do this in different ways, but for this particular engine, I chose that I didn't want to have to dynamically put data into the GPU. I wanted all the data to be loaded into the GPU at once, so I wouldn't have to worry about it. So there's a lot of work put into compacting that data in some way. And that limits things. It can look better than what I was showing here, but if we actually look at this up close, and again, I apologize for the thing, you can see that there's this artifact here of the boundary on the ground between the two different ground types. And what that is it's just a grid. It's a grid of 16 by 16 voxels. So the entire world is divided up. The entire map of 64K or 128K voxels is divided up into whatever that is over 16. So 64 over 16 is 4K. So the inner area is a map of 4K by 4K tiles. And each tile for the ground has this height variation and a color variation. And then there's also a height field that's added to it. So that the height field allows the smooth variation and etc. So the plan is to hide this seam by having either ground types that are mixed, that are a transition between the two. That's a well understood thing in 2D, or even an object layer on top that like smoothly fades out one side and not the other, something like that. Just never got around to any of that stuff. I actually did start writing some of it, but did never actually put any of it in. And of course, the performance thing meant I didn't pursue it further. So the ground does that. And the ground is then very easy to LOD because you just average the heights, and because the ground is always fully extends below whatever the height is. So you just average the heights in a 2x2, and average the colors. Maybe that's good enough. And that's how you LOD the ground. In general, the thing works by, you could think of it as CSG. But the idea is that in each column, there are multiple what I call layers. There's a ground layer and there's object layers. And they can intersect each other. So these trees are poking into the ground, actually. And that's fine. The system resolves it. The system figures out which thing does it hit first, ground or a tree, and draws the right one. And so it allows this totally arbitrary level of overlap. So we divide the map up into these 16 by 16 tiles, and each tile we get a description of the ground, and we get a stack of objects. So they're object fragments that are 16 by 16 by however tall. And there is a height limit. Maybe 256. I don't remember. Oh no, it's a weirder thing than that. Yeah. Anyway, so in each tile, there is some data that says, here's what ground texture to use, here's what ground bumpiness to use, and here's some info about the objects, and here is the height of the tallest point of any object in this tile. And so when the ray tracer is traversing, it can say, before I load anything else in this tile, let me just load that little bit of data. And that data is going to tell me the highest point of anything in this tile. And if my lowest ray in the packet that I'm tracing is above that, then I'm done with this tile and we can move on to the next one. Now I can't move on to the next one until all the other lanes, SIMD lanes in that job have all agree that they're done. So this only gives you a speed up if all of them skip. But when you're like tracing in the sky, like most of these rays are above stuff most of the time, and so they get to go very fast. And in general, I think no, I don't have that version here. I can actually visualize that. I have a thing to visualize it. So variant. Oh, I'm in the wrong. That's why. Variant test. Not that one. visualize height bound, and then turn off all the other variant tests. Yep, okay. So if I do this, then what I can do is if I toggle that variant test on, it will draw the ground where the height bound is. So the ground jumps up to cover the height of all the objects in it. And so this is what it's testing against to early out. And so as long as it's not hitting any of these things, as long as the ray step is not hitting any of these things, it gets to go very fast. And as long as it's a little 64 by 32 chunk. And you can see that at least with this data, you know, it's great. Now, if you put lots of stuff high in the air, which I haven't done in this demo, it can't do this early out, and it'll have to test the data, and it may be able to still say it doesn't intersect anything reasonably quickly, but not as quickly as that. So it's definitely an engine that's designed to say, have stuff near the ground. So for example, one thing I was thinking about before I was thinking about Factorio, I was just thinking about this being a general purpose outdoor engine. And so I was thinking, well, you know, maybe you have power lines, but actually you just draw the power lines with polygons. You don't draw them with voxels. You draw them as voxel shapes, but with polygons, and don't go through the ray tracing engine, because that's, you know, we can see that you can put polygons in and they you know, z-test against the stuff, sort of. It's not perfect. But better than nothing. And in fact, one of the motivations for this engine originally was thinking about PUBG, Player Unknown's Battlegrounds, where one of the things that happens in that game is that there's grass cover and you can try to hide in the grass, but if somebody's far away from you, the grass stops rendering to the LOD and you're totally visible. And I was trying to think about, could you make an engine where even when you're far away, and so here's a zoom, I'm zooming in. And so you can see the bottom of these guys is still hidden by the grass in the distance. And this is actually doing bad LOD stepping. Like I haven't adjusted the LOD stepping correctly to account for the camera change. So it's actually taking pretty big steps there, and it still works. So anyway, I don't remember how I got on that tangent. I think you make the player invisible if the grass went away. Yeah, but they don't. Like, that's not what they do, and it's hard to see how to do that. And what if they're partly in the grass and partly not in the grass, right? So like just making an engine that can do it right is kind of cool. Oh yeah, so I was talking about the polygon stuff. So you know, the idea is you want this dense stuff to be ray traced so that it is just always present, but sparse stuff like power lines you could do with polygons, exactly align them to the world. You wouldn't be able to tell that they were polygons, but there's no reason that you have to actually make them be ray traced. And so that sparse distinction is what I was thinking about for tall things. Now you can make a building, and that building would be fine, because, you know, when you do this to the building, okay, yeah, every ray that, you know, gets to the building has to traverse the building. And yeah, the rays that would go through a window on the front and out a window on the back, those rays have to do extra work to process the building, even though they don't hit the building. But that's fine. Like, that's the kind of work you expect your ray tracing engine to have to do. So that's that. Right, so I was talking about the map. So here's all the data that's in the map. Let's go to the document for it. Is that in ideas? Is this the most current one? I don't know if this is the most current one. We'll see. We'll see what the most current one is. So actually, yeah, I made the height band, actually I made it sparser so that you have less data to load, because we do actually hit that a lot in this model. And so as long it loads it every tile, it doesn't try to say, oh, I'm still in the same 2x2 tile I was in. It just loads the texture, the height band from the texture. But it's it loads the height bound from the texture, right? But the texture cache, the GPU has a texture cache, so the whole thing is to minimize misses out to main memory, and so or not minimize, but reduce them. So by doing that every 2x2 tiles and making it a totally separate data structure, so that's the only thing I load. Outer tile info I think is gone now, but There's outer tile. Is that outer tile info? Might be. Yeah, and then this is some stuff I started doing for the Factorio stuff. But so here's info about the terrain. So if you're in the 64K by 64K region, your terrain tile is 18 bits. You get 2 to the 18, which is 256,000 possible ground cover tiles, which is a lot, right? So you can do a lot of those transition things and variations on them and all that stuff. I didn't do any of that work, but you can do that. Yeah, the Windows 7 is more and more stuff. More and more apps, I can't upgrade their apps. I tried to upgrade OBS when I started the stream, and it won't. They don't support Windows 7 anymore, so I'm still on the older version of OBS. And that's the answer. I don't upgrade versions. So there's this 16-bit thing that we have for the whole map. So the whole map is 8K by 8K for the big full map, but we only get details in the 4K by 4K region. So I was doing this thing of like trying to say, well, let's have less info on the outer one and more info on the inner one. But it turns out this one's 16-bit and this one's 8-bit. So the savings you're getting by only having this on the inner one isn't that great. But so the outer one, you can't rotate the terrain tiles. And the inner one, you get a 2-bit rotation of the terrain tile. You get 18 bits of terrain tile data, whereas you only get 15 for the outer. And there's this thing, which is tile instances is terrible. It's the number of objects that you have in the tile. So in the outer area, you can only get 1 object per outer tile. So you can still put like trees down, but the trees have to be a little bit sparser because if they overlap each other, you have to use multiple objects, right? So the idea there was a tree, every 16 by 16 chunk of the tree gets chopped up and created as its own conceptual object. And then you put down the right ones in the right spot. And as long as the trees don't, their trees bounding box can overlap, but the object, their leaves not overlap, even though the bounding boxes overlap. And so you actually end up with multiple objects in each thing. And for some reason, this test world, even though the objects don't seem that dense, as I recall, was there are some tiles with at least 4 objects in them. I don't know how that happened. I didn't dive down into it very hard. The performance, if you turn off the trees, the performance still doesn't go down to the 4 milliseconds. It's like nothing to do with that. And the trees predate that problem anyway, but just in case people are wondering. But so the idea is, so there's a height field that covers the whole map, and the height bound. There's that outer tile info that we're looking at, which gives you 15 bits of terrain info, the 8-bit inner tile info, and then you have descriptions of the objects, and those are just a whole bunch. They're not packed tightly. Each one is a separate map, so you get up to 6 objects currently. I think I originally allowed 7, and it just loops over them and fetches each one. A lot of that stuff is designed thinking about how it works when all the lanes are in different tiles on the map. So you always make sure all of the objects are packed at the lower numbers. You don't, even though there's six layers of objects, you don't allow there to be an object on layer 5 unless there's an object on layer 0, 1, 2, 3, and 4, so that when the wavefront is marching through and it has to keep looping. Oh, well, this one has an object on layer 3. Let's loop all the way up to layer 3. It's only doing that because there were at least 4 objects in at least one of those things. And probably other ones are nearby and it might be a similar density. It works okay. The ones without an asterisk, I haven't coded yet. So there's this thing to just do a little bit of coloring. So here's that thing I was saying. There's a 64K by 64K by 1-bit quote unquote texture to do the ground shadows. And that is actually the single biggest data structure in the whole thing. It's 512 megabytes. Let me check the chat. Okay, people are talking about Win 7. And then I haven't done any of the other lighting work, but there's ideas. Then the terrain chunk, as I said, it's a 16 by 16 tile, so that's 256 here, and it's an 8-bit height. It's actually a signed 8-bit number, so you can go above or below the default height, and that's just a little. It works out the same either way, but it just makes things a little simpler. The color of those tiles, because it's a 16 by 16 tile that corresponds to the ground tile, you probably could do something like BC7 okay, but I don't have a BC7 encoder, and I do have the raycasting STB-DXT thing, and if you use that in BC4 mode, it's actually pretty decent quality, even though it's a runtime thing. So I just use that to oh, and that's that step that I was trying to fix the contrast goes through that. So maybe that's why that wasn't working. At the moment, I've coded this as if there are 2 to the 20 possible tiles, even though there's only 2 to the 18. Right? 1 million is 2 to the 20. So I guess I've been tweaking these numbers and didn't ever tweak that one back. But and there's a bunch of things like how to make this work with the outer tiles not having rotation, but you need everything to line up and look okay. And so that, and I've never done any of this work, but the basic idea is like, suppose you have a transition tile and you'll need 4 rotations of it. What you do is you'll make something like 32 variations of it, and you'll pre-rotate them in each of the 4 possible directions, some of them. So like, so there's 32 of them. So 8 of them get pre-rotated one way, 8 get pre-rotated another way, 8 get pre-rotated the third way, and 8 get pre-rotated the fourth way. And then you can access those from the outer tile info without a rotation and get those. And with the inner tile, you also get the rotation, so you get more variation. And, once you have a rotation on top of that, it doesn't matter that it was pre-rotated. It's as if it wasn't pre-rotated. So you just have 32 variations that you can rotate any way you want. Plus, it gets more bits, which you can use to put more custom stuff in or to have more variations. So maybe the outer tile only gets 16 variations and the inner tile gets 32, or something like that. So there's a bunch of stuff that you could do with this. I never got to any of this stuff. Back to this. So yeah, so I do this as 3 separate textures. Haven't done this thing about some more lighting info for them. And then those objects, which are just the trees right now. So the way it works is we store in the map a 32-bit object reference, right? So we have, for every tile, we have a 32-bit number. And we look that 32-bit number up in a table for, in this table, we index into this table. So there can, even though it's a 32-bit number, we only support 128K of them. No, this is the span reference. Span array? No. Object texture base offset. Gosh, I have to look at the code. I don't remember now how this works. Let's see. Oh, there is one more thing I wanted to talk about the rendering. So the ground tiles can't be concave ever. The tile rotations are just on the map tile, like swapping around X and Y. So there's just 4 rotations. It's just standard 2D tile stuff. Which, yeah, I mean, you may not be familiar with, but like there's all these classic things you can do in rendering 2D stuff. And so ground is basically just 2D with bumpiness, displacement. What was I going to, oh, so the one thing I want to talk about the renderer that I forgot to talk about is, so when we find that array ends, we store some info about where it ended. We store like, where was it on the map? What was the array it ran into? Do we store the color? I don't think we store the color. I think we store the offset. We say we were on this span and we had this offset, etc. And we write that out. Then in the main loop, we're stepping through the map. Okay, so here's the main loop where we step through the map. And every 256 we do some special work, which we're not going to worry about. It's LOD related. And then we do a bunch of stuff and we test if we're visible or not. And then we test against all the objects, and then we test against the ground as last. And we write out this info if we did end. If we ended, we write out some info. It goes into an image. And then we set that ray is not active anymore. And at the top of the loop, we check if active rays is 0 and we exit. Once we exit the loop, if we ran out of steps, then we'll still have some active rays, and those should show the sky color. And we'll do the sky at the bottom. But first, we loop over all the rays that we did hit, and we figure out what color they should be. So we do the shadow lookups. We do the texture lookups to figure out what color they are, et cetera, excuse me. And the reason that's done last and not as part of this ray stepping is to do with how GPUs work. Because on the GPU, we're going to have a single SIMD lane that's like, oh, this SIMD lane, three of its rays collided. And on all the other SIMD lanes, none of the rays collided. Well, now we're going to do some code that's going to run for all the SIMD lanes, and we're going to have to loop over all of the rays that ended. So we want to do as little work as we can because we're wasting time for all the other SIMD lanes. So we just immediately store out, we pack all this info up and we store it out, we clear the thing, and we do as little work as we can. Which part of it is not smooth or perfect? The artifact I talked about, or or some other thing that you're seeing? The artifact I talked about that you can't see, or some other thing you're seeing. So we do as little work as we can. Then when we get to the end, we say, well, all of the rays that have been finished for this SIMD lane, let's process them. And that's going to be most of the time all of them, or if you're looking up in the sky, none of them, or if you're at the horizon, some and some not. But assuming none of them hit the sky, it's going to be all of them. And that means all of the SIMD lanes are going to process all of the things in lockstep. All of them are going to have 32 rays to resolve the color and the lighting, and they'll all do all the work in parallel, perfectly utilizing the GPU. So utilization, that's the word I was looking for this whole time. So we get 100% utilization if we do it this way. You can also do it by having separate shaders, right? We could have the compute shaders write out where did they hit everything into a buffer, and then run a separate shader that's like, okay, now let's resolve all of those things, a bit like how deferred shading works. For various reasons, it's both simpler to keep track of, to do it all in one function. It used to work in a different way where I used local storage, not a big texture. So you had to do it this way. And it also means there's a little bit less info to write out, or info that you would have to reconstruct. So it's actually a little bit better. The SDB voxel just renders everything as polygons, so everything is, there's none of this hackery. Would overhangs and their ilk in the world typically be assumed to be polygon-based? No, because these trees are overhangs. So if you wanted to build ground-based overhangs, like if you wanted a cliff that had an overhang, you would build it as an object, but the object is still ray traced, right? These objects are still being ray traced. And so you could have an overhang in the world where the geometry steps out. The lighting wouldn't quite match because it wouldn't have the ground shadow info, correct? It would have its own cast shadows, but you could actually bake out unique data just for that overhang. So like here, you could overhang by just building a little object that sticks out. And the plan had been to have the editor do that for you automatically, right? You would sculpt out a little shape that you wanted, and it would do that. The GPU is shown in the top left corner. It's a GTX 980 Ti. So that answers that question. What was I talking about when I was saying that? Right. So we get 100% utilization of this step, and this is sort of an easy way to do it. It was the way I had to do it originally. It's not worth switching it back over to doing it as a separate step. But that's why this stuff doesn't try to compute the color immediately, because it would be, all the other lanes would potentially be sitting idle, and so it batches up all of the next phase that's going to do. It's batching up all the work for that phase to do and doing as little effort as it can to batch it up. So it avoids fetching at most things. Well, the ground is a bad example. We want to look at the objects. That's a little more complicated. Process instance, then it steps into process span. Oh, right, because I was looking for how the indirections worked. So in process span, how much work do we do? Yeah, we don't do any extra work to compute this. These are all values we already have at the time we got here. So like, we need to know the tile ID to know what thing to fetch the right texture, but we just store how far offset in the texture it is and leave that for the final step to do that work. Okay, so I've been saying, I was trying to explain the data format. So how does this indirection work? So we get an instance, we look up in that table. What do we look up? All right, so the object has the height that it's positioned at vertically. So we have to extract that. And then we take the position in the tile and we fetch from voxel tile data. I don't know how that corresponds to this description. It's a uint, so it would be 4 bytes. Maybe it's a span reference and this is misleadingly named. Yeah, because this one is by 256, so it's got to be this one. Okay, so to process the object, we're iterating through all the objects in the thing. We load the description of the object from this thing. That tells us which object it is and its vertical position. Yeah. Ignore the shifted thing. That's just a complication. So this tells us the rotation of the object, what its height is, and which object it is. And by object here, we mean a little 16 by 16 slice of an object. So we're limited to how many we can have. There can only be 128K of them, right? 17 bits. So we can't have that many different objects. That's just how these bit sizes let us do if we want to have a good range of vertical positioning. And we want the data to fit 32 bits. So then we fetch that. We fetch the correct position in that to get a span reference, which is a pointer into our span array of the different spans. Or if the object only has one span, it may just be that span directly to save an indirection, which saves the load. Even if some SIMD lanes have to chase the indirection, some don't, you still save loading the memory. So even though you have to stop it regardless, it does reduce the memory traffic. The span reference tells you has a pointer into the span array and a count, so you know how many spans you'll have to pull from it. So it doesn't actually store the transparent and the opaque the way I said. What it actually stores is where the span starts and where it ends, except it might be relative actually. So it is effectively the thing. Then the span array stores, each span stores how long the thing is and an offset of where the textual data for that span is, and that is relative to an object texture base offset, so that because that span, it's only 15 bits, and then so each object can have up to 32K. Actually, no, I think that's scaled by 64 or 32. I forget. So each object has a limited number of little runs of colors it can use, but it can reuse them if it's got copies of similar data. Like one thing you could do is pre-rotate objects, although I think we support rotation. And if you were pre-rotating objects, each, again, only talking about rotating on the map XY, then each rotation is still going to use exactly the same set of spans. It's just shifted around where it is in the array. And so you could share all of that data and wouldn't need any redundancy of that. But I think we support rotation. This version of it claims we do. I don't know if I ever coded it. Process instance. So each instance would be, yeah, no, it's using XY pods, which is pre-rotated by the caller. So it's, I don't think it rotates them. But I could add the code to do it, obviously. So you could do it either way. Anywho, so that's like a quick overview of how it's stored so that it can be compact, fit in 4 gigabytes. So each of these chunks is under a gigabyte, and there's 4 kinds of data, basically. And that lets you do a much richer world than what I'm showing here at a large scale, but obviously it's all repetitive, right? All of these things are tiled, and those tiles appear many times on the map. But there are, 256,000 unique ground tiles. So, and there are only, 4K by 4K? Well, that's still a lot. There's 16 million. So in the main area, there will be 16 million ground squares. And the data for that, there are 256,000 unique ground tiles. So the idea is you would predefine like half of those, 128,000, to be the generic stuff. And then you would have the other 128,000 customized to this map to do specific things. Or if I don't want to allow user editing. This system was designed to not allow user editing, but the map designer can put down custom stuff, sculpt the terrain in custom ways, make custom transitions, and the editor would just create extra ground tiles because it's got this huge space to store another 128,000 ground tiles. So it can make custom ground tiles, make ditches, make all sorts of stuff. But anyway, so yeah, and so to sum up for people who didn't see the beginning, the whole point of this engine is that I had it running on this GPU 4 milliseconds a frame a year or 6 months ago or 9 months ago or whatever. And then it stopped running that fast for mysterious reasons that I could never figure out why. It's now running at 11 to 12 milliseconds per frame, which is still fast, but not as cool. Like there was so much you could do when it was running at 4 milliseconds a frame that implied about how much more built out you could get beyond what we're currently at. And still on this GPU, 980 Ti, which is a high-end GPU from 2016. So, depending on where you're willing to draw the line on what you allow, will require lower sizes. But if, say, you were targeting around a 980 Ti, which I don't know what that is on a today's thing, a 1080 isn't that much faster. But if that was what you were targeting and you were hitting 4 milliseconds with that, then you could make, tall buildings and all sorts of stuff, and it probably would still gonna fit in 16 millisecond frames. But since it stopped working, I don't know. I gave up. It's still a high-end card. Okay, yeah. But I am also running at a decently high resolution, right? I'm ray tracing at 1600 by 1600. So, obviously if you want 4K, it's, 4K is what, 4,000 by 2,000. So that 4 milliseconds would scale up to, 10 or 12 milliseconds. So if you want to run at 4K, you'd need one of these cards and the old fast version of this. And about the same level of complexity. But that's okay. My goal was never to run at 4K. My goal was to enable a high complexity. Oh, yeah, so let's talk about a trick. Fun trick. Let's not do it in the game. Let's do it in the Milton. That's not Milton. Where's Milton? That's OBS. Did I close Milton? Apparently I did. Unless oh, that's Milton. Okay. Um, so, uh, so we're drawing a column of pixels. And the way we do that in practice is, so here's the column that we're stepping into. God, I wish I could draw straighter lines. Just like shift to, I think, no. So here's the column of voxels we're drawing into, and we're not saying what's in them yet. We're just talking about the space. We're traversing the space. So these rays come in, and again, as I was saying, the right way to think about it is not that the rays step like this, but that the rays do this. They enter here, and they exit here, and they enter here, they enter here, and these are all linearly spaced. Well, that's not very good because I didn't have any of them hit the top and bottom. We can actually have them be more compact even. So this would be like this, and this would be like this. So the rays are doing this. So I still managed to miss. Oh no, here's one. Okay. Oh no, I matched them to the wrong one. I should start at the bottom. So these are the rays that we're processing when we go through this column. And again, what the actual implementation just computes the entry and exit points is all you need to do the math to do it. Because you don't actually need to know this intersection, these intersections, which require the rays. You just need to know which of these are solid and which are empty, and you can figure out whether it's hitting the front or the bottom. So what was I going to be talking about? I don't remember what the point of this was. What was this? I never said. I didn't tell you. So now if I can't remember why I went into this, shoot. Dang it, what was I going to talk about? A trick. What trick would there be here? Dang it. A super secret trick. Well, I mean, you know the big trick, right? Obviously. It's the GPU thing. So what could this trick have been? What was I looking at? I was thinking about the size of things, number of bits. No, I don't think it could have had anything to do with that. Oh, that's so annoying. Oh, my brain. Why did I forget what I was talking about while I was explaining? Oh, yeah, I can't figure out what triggered it. That's what I was trying to, that's why I was looking back at this, trying to think what was I thinking about that triggered it, but I honestly don't remember. Like, I'm sure if I heard what I said, 4K, size, speed. Oh, okay. It had nothing to do with any of that stuff. It was part of the data format that I didn't talk about. Okay, so one possibility is that we have, let's get a new color. One possibility is that, there's a span like this. Let's do it like that, right? Because it's in this column. So this one is green, and this one is green, and this one is green. And we look at these dots, and we say, okay, this ray is below the bottom. It doesn't intersect. This dot is below, but this dot is above the bottom. And if the beginning is below and the end is above, then it hit the bottom of this span. We're not testing the individual voxels. We're testing the span. This one, the entry point is within the span, so it collides on entry. This one, the entry point is in the span, etc. This one, the entry point is above the span. It's going upwards, so we are done, and we don't have to test any more rays above it. So that's the sort of algorithm for that. Now, when you have stuff like these trees, and before I put in the trees, I had these, I did this. I don't remember if the trees actually use this or not. But the trees are these really sparse things, lots of little short runs. So there is a second kind of span in this, that the length is always 32, and that 32 length, actually, I think it can be a different length. But that thing, let's make it larger. Let's say it's here. But that span comes with a 32-bit number that is a bunch of ones and zeros that says for each span, for each voxel, whether it's present or not. So it lets you have a sparse voxel span. And that's good for things like those leaves, maybe. I tested this with some hard-coded data where I just generated these at random. And I don't know if I ever actually tried to synthesize them from the trees. So the trees may not actually be using it. But now we have a problem because we want to do this testing without testing this stuff. And it's definitely not as efficient, but it's still more efficient than if we made all these be individual runs. So what we do is, how did we do this? Does each ray test, or does each... So there's two different ways you can do this. You could either say this solid span corresponds to which rays. So you could iterate over this and find the solid spans and then say which rays does it overlap. Or you can go over each ray and say which the spans does overlap. I believe what we do is we first say which rays overlap the span at all. And then if the ray overlaps the span at all, in like with the old testing basically, which in this drawing they all do, then it projects the entry and exit points to find out where they lie in this. So it says this ray has to test against this one. This ray here has to test against this. This ray has to test against this. And eventually they have to test against a bigger run. But they can test against these in parallel, right? It takes the entry and exit points, and this one, this exit point, it generates a bit mask that's like 1, 1, 1. No, wait, 0. So the entry point generates a bit mask like this. And then the exit point generates a bit mask like this. Or this one, we generate a bit mask like this. And this one generates it like this. I forget. I don't remember exactly how to draw it. And you XOR this. So one corresponds to the bottom entry point and one corresponds to the top entry point, exit point. And you XOR the two together. And that gives you a, sorry. Yeah. This one, the XOR is that. And this one, the XOR is this. Or, sorry, this. Jeez. And then you can test this bit pattern against this bit pattern and see if they overlap or not. So you can get a quick reject. You still have to test each one individually, but each one just does a couple bit operations, and that bit operation lets you say, did it hit a voxel somewhere in here or not? Once it did hit a voxel in here or not, you now have to use a find least set bit or something like that to find the right one. And I don't even know if I did that all the way through. Let's see. So it's in span, process span. Where's the one where we do, is that like a separate? Ah, yes, process sparse span. So you walk through all the active rays, you figure out where they correspond to. I actually use this bit field insert instruction to generate the thing, then check if they overlap. If they do overlap, you find the MSB or LSB. So it's still, you still have to iterate over every voxel, every ray. Yeah, you're tracing 32 rays in parallel. In the old code, in the normal spans, you still have to test each of these individually. The normal stuff is you just say, oh, like this. And for this stuff, you can determine which ones overlap in mass, but I don't bother to. I test, does this one overlap this one, etc. I think maybe to find the entry point I do it right. I don't remember. But because, as I said, if they do overlap, you have to do a bunch of work per ray anyway, because you have to write out the description of where the ray terminated. So you might as well iterate over them, and then you early out once you get off the top. So with the sparse stuff, it's the same. You iterate over all of them, but maybe you don't write anything out, because maybe you determine, oh, because it was sparse voxels, it didn't hit anything. But eventually you get past the top and you can early out again. So it's doing more work per step because it has to do these bit masks. But it's not like an n squared kind of thing where, oh, I have to iterate over every ray and every voxel. And the iterating over every ray that you have to do, you were already doing even with regular spans. So it's not an extra layer of things. So it works out to be, not as fast as regular spans, but faster than a couple spans would be. So as soon as you have, if they fit in 32 voxels, if there's a 32 voxel stretch with a couple of voxel spans, it's faster to use the sparse data. So that's a fun little trick. And depends on your data. Like, do you have sparse data like that ever? Like, maybe you don't. Like, if you make a building, it's a big flat wall, like, and inside it's furniture, it's not sparse. You should build everything solid, by the way, in this engine. Like, the interiors of things should stay solid. In some engines, you hollow them out and leave them hollow. Like, I don't do that in OBBG because you would have to draw polygons inside there potentially, or you would think you would have to draw polygons inside there. But some engines do that, and in this one you don't want to do it. Isn't this only an improvement if all don't hit? The hardware there is still run 32 wide. Anyway, well, I mean, this is all okay. So remember, you may have missed if you came in late. This packet is all one lane of the GPU job. This is one SIMD lane, and other SIMD lanes are processing totally different spans, and they may not be sparse spans. And if they're not sparse spans, you actually run the sparse span code once and the non-sparse span code once. So in that sense, it's not efficient. But so the whole point is that the iterating over the rays, one lane is now iterating over multiple rays, and the point is it has to do that for both kinds of spans. So it's not less efficient than normal spans, but that's a whole separate thing of it does have to iterate over the rays, but it would have to, and that's the whole argument where it would have to iterate over the rays anyway. All of this, yes, if other lanes don't hit a span at all, like this is all wasted work. Like your utilization is not necessarily that great in this engine. All I can say is, with this data, which obviously is very structured, it's like all the stuff is on the ground, you're hitting trees everywhere all the time, so many of your rays are doing similar things. But there are, like I said, in some of these tiles there's 5 objects or 4 objects because due to how close the trees get together. Like here in the middle you can see the trees overlap, but somehow it manages to, oh, that's a great one. Another busted one. But all of the so anything like that where you're iterating over all the objects in the tile, if some of the rays packets aren't in a tile that has multiple objects, all of that is wasted utilization. It's just better than, like, this is the thing I found that works well. Now, and of course the important thing to remember, did I actually close it this time? It was yeah, apparently I did. Weird, because wouldn't it have asked me to save or not or something? Well, it still had the data, fortunately. Um, what was I saying? Uh, oh, sorry. I accidentally hit the wrong button. What was I saying? Yeah, I've totally forgotten where I was. Cause I got distracted by fucking up OBS and all that. Um, I literally have no idea what I was talking about. So yeah, remind me. Screen lane, GPU lanes. Um, the GPU utilization, it's bad. I don't remember. I don't remember what my. I remember the earlier point, like the last. I can't remember a point I was on, but I don't remember what point I was finally. But anyway, so the point is, at least, so this little trick, the whole thing is that these sparse spans aren't significantly worse than the regular spans. The regular spans require iteration as well. Obviously, requiring iteration is inefficient, and it's the number of objects times the number of spans. So if other lanes hit fewer objects with fewer spans, or say lane 0 hits a tile with one object with 20 spans, and lane 5 hits 5 objects each with only one span. Well, first they're all going to process object 0, and the first lane is going to have to process 20 spans, and lane 5 is going to sit idle for 19 of those spans. And there's stuff you can try to do. You can try to write code in a way that's like, let's flatten that. Like, let's allow every time you step, you could step to a new object, or you could step to a new span. You can try to write that stuff. I have not done it that way. Oh, I was just saying, with this data set that is all very similar. But and so maybe with other kinds of data sets, it would not be as coherent. However, I expect within a small region of the screen, they're not going to be in the same tile, but they are going to be in adjacent tiles or whatever. And if adjacent tiles have similar data, then you're good to go. But if you do start mixing objects that are 16 by 16, because remember, one of the tricks here is that the object is bigger than 16 by 16, and it's getting split into little sub objects, and each tile, is that. So if each of those objects is still very similar, and they're in the same spot in the layer hierarchy, then everything works great, and the coherence is going to mean they're doing similar processing. I don't do any transparency. You would have to do that stuff as polygons. Like if you wanted to do water, you would just draw that as polygons. Like the whole thing is, this is an intentionally limited engine. This is a classic rendering technique with software rendering. It's an intentionally limited engine that can't bank, can't do certain things, totally fakes its vertical tilt, but to a degree that's not. Oh, what was the follow-up on that question? Somebody asked about the warping, and I asked which warping he meant. Oh, that's right. That was the thing where he said he was talking about a different engine. So yeah, and it doesn't do transparency, much like a deferred engine doesn't do transparency as well. So, as I've demoed, you can rock solid draw polygon stuff. Even though my polygon stuff, because of historical reasons, the voxel scale isn't the same. You can put them in. They do not quite Z-buffer correctly against the terrain. So if they interpenetrate the terrain, they won't be perfect. But you can, so like if you did them for water, then the places at the very edge where the water happens to line up with the voxel at the edge would potentially do something weird. However, that's just because like I never tried to get the math perfect. Like I'm sure you could go in here and get the exact perfect location of the intersections and get the correct Z buffer. What I do is remember I said I never figure out this intersection point. Instead, I just say, oh, what's this? Oh, you're hitting the bottom of this ray. So I say, oh, you hit the bottom of this voxel, and I store this. And so then when I go to generate a Z buffer for the rays, I store the Z distance of that, not of that. And so that's why you get that little bit of intersection goofiness with the polygon objects with the guys, which we can go look at again. Where they're basically Z buffering against the ground, but they have little artifacts right like that. And I'm okay with that. But because you would have to do more math to get it better because it's just using the center of the voxels. But it might be so the way it does this is it generates for every ray the Z distance effectively. As a Z, so a quote unquote Z buffer, but it's just in a regular texture because the way Z buffering works in engines, the speed ups come from having things like hierarchical Z, which it needs to have written it as a Z buffer using polygon rendering to compute correctly. And on consoles, it's possible to get really access and like be able to build the hierarchical Z buffer yourself, but I can't do that on a general purpose API like OpenGL or D3D. So I can't do that. So I don't build a Z buffer. I just build a texture and I look up in the texture and do a comparison directly in that texture. So to resolve this thing better, currently it's looking at the actual Z of the polygon guy and the Z of the center of the voxel, even though the voxel is visible much further forward. So in that comparison, I can't do anything about the position of the voxel. I don't know where on the voxel it was anymore, and I don't want to store enough info to recover it. But actually you wouldn't need any extra info because you can use the ray direction and that correct voxel distance and which face it is, and you could recover it actually here in that chair. But the easier thing to do is to take the polygon position and snap that to the middle of the voxel and use that for the comparison so that they're both using the same snapping to make the decision. And that way it would be consistent. Why use OpenGL DirectX if there are really only AMD to program to anyway? Intel now too, but also what do you use for NVIDIA? Like AMD, what do you use for either of those? AMD used to have Mantle, but I don't know that they support that anymore. You can use Vulkan, but how is that going to make any difference for this? From a shader perspective, Vulkan and OpenGL are essentially identical. Like only on consoles do you get low-level access. You don't get low-level access on PC ever. So you can't do any of that stuff that I was talking about that you can do on consoles. But anyway, so you could fix all this stuff. Two different ways you could fix it. Again, I'm not working on this engine anymore. That's why I'm sharing all the details, because this is done for me. I don't know how to fix my problem, so I'm done. It's sort of. They took some inspiration from it, but it was still a new design, I think. Oh, sorry, I forgot to say the question before I gave the answer. My apologies, but I'm not going to go back and do it now. But anyway, as you can see, that perspective hack works totally fine. Like as I said, even when the voxels are very steep, or the rays are very steep, it does do the correct calculation. You just can't quite tilt all the way to 100 degrees, and you can't see the artifact because of the low contrast. But yeah, that's not even enough. You have to do this with the trees to see the artifacts. And this you just have to crop it a little different. Like this just is me not limiting the tilt enough. I'm allowing the tilt to go a little too far. I guess if I got under a tree and looked up, it might do a similar thing. Yep. Yeah, I mean, you can see the sky is even just wrong. Anyway. Yeah, and that, by the way, that sky was just a debug thing, so I can see how far the voxels are tracing before they hit the sky. Because how high you put the sky determines how quickly the voxels stop, and I was trying to figure out the performance issues. Oh, and so yeah, here's the edge of the map. Wait, M, that's how you go really fast. Here's what's past the edge of the map. I tried to set all the textures to wrapping or so that they would just repeat, but something isn't right, and so it just has nonsense data out past there. I think once upon a time there was actually a second copy out a whole distance away that you could get to that sort of rendered right from the distance, but anywho. So yeah, this is that whole thing of, because it all fits in memory, you can fly really fast, you can teleport, and because it's all in memory, it doesn't have to do anything to load. You could just absolutely teleport and nothing would. You could teleport every frame and it wouldn't be a problem, which is a solution in search of a problem, right? Like what game design needs that, but it does mean you could fast travel on this map with no time delay. Is this map proc-gen or static? This is static. This is actually a DEM file, which is a digital elevation model. So this is from some part of the US. I don't remember where I got it from anymore. I actually had one that I loaded that was the Grand Canyon at one point, but I don't think that's this. And then the trees are all randomly proc-gened, but statically, like, so it's the same every time. Yeah, you could certainly do random maps. It's just that's a problem I tackled in OBBG and what's kind of frustrating. And so because it's tile based, it does mean you don't even have to work at the voxel scale to generate, right? You get to generate at the tile scale. And so it's all totally feasible to do. But it's not, I don't care about trying to do that for this. I certainly, if I were to do the Factorio game, I would have it be proc-gened, but I'm not doing the Factorio game. Okay, this long quote. Orthrax, you'd have to expand on what you're imagining happening, because you need to resolve you only have room to store a single voxel's worth of information per array. So I know I didn't explain the question, but that's because I want him to expand on his question before I try to. So if you try to do anything funky there, like what are you storing for that array to recover the voxel information, or how are you structuring that data that you're storing, and how do you know which rays to keep extending, because you need to stop, and the only way you know to stop is because all the rays have hit stuff. Yeah, the portals that instantly teleport you around the world is definitely one of the a problem that this could be a solution for. Of course, you don't have to use voxels to do this. I had a whole design for a big outdoor map in 1 GB, where everything was polygonal, instanced heavily, height fields, instanced trees based on with an explicit tree map. But that was, no, how did that work? No, because it was still all in the GPU. You didn't have to update from the CPU. So it was just pre-stored data per, megatile, whatever you want to call it, like, a big, a 1 kilometer by 1 kilometer chunk or whatever would have, you know, the trees in the trees were on a finer thing than that, so you could LOD them properly. But anyway, the whole point is like there are other engines you could do that do that kind of thing. It's just its whole other problem of you have to figure out how do I compact all this stuff? How do I pack the instancing data? How do I pack the geometry data down? And that's what this voxel engine is doing. It's all instanced effectively, and that's a solution that you can do without being a voxel engine. I just happened to decide to try to do that for this voxel engine. Oh, and I never explained one of the reasons why this structure came about. I was originally doing this as a polygon engine, this design of how do I do LODs and having these what I called layers, which is, you know, you have the ground layer, which is actually vertical layers, but I mean layers like sort of conceptually, like in Photoshop layers, which is that you can put 5 or 6 objects per tile, and those objects can intersect each other. That's all fine. They're not physical layers stacked up, but they are, you know, fourth dimension layers. This is actually how the Thief Dark Engine editor worked. But the idea there is that each layer knows how to LOD independently. So, you know, this tree knows how to do its LOD, and this other tree knows how to do its LOD, and then you take the intersection, the union of those objects LODs as the LOD for the thing just automatically, because each one just LODs independently, and the engine itself is doing a union when it's, you know, in each column it's saying, let me test against all the objects in this column independently and take the first hit. And that's equivalent to a union. It's equivalent to using a Z buffer and drawing multiple things, and you get whichever one that gets hit first. And so the idea there is just that by doing the ground separately and each of the objects separately, if there's a billboard, which is very thin and has certain rules for how you want to LOD it, like I was saying, instead of having an algorithm that tries to take the combined thing of everything and do the right thing, instead the algorithm takes each individual object and figures out the right thing, and a human can intervene and say, no, this is a doorway and I want the doorway to actually get bigger, because normally what happens is the voxels expand. You tend to expand the voxels to fill the space. Like, you know, if only one voxel was filled and you do the LOD, you may still put a voxel in there. But, oh, no, this is a window or a door. Let's have that expand some of the time until you're really far away, so there's always still a little hole in the object. That was the idea of the LOD, and it started actually on a polygon engine, and then I came back to this idea that I had many years ago and said, hey, let me try doing this engine with that idea. Let's see, Horthrax. Essentially the LOD test again. What thing are you trying, Horthrax? What thing are you trying to avoid doing in the raycast? Would it be possible to animate the trees a little, make them sway in the wind a little bit? Would the engine allow this? In most senses, no, because all the voxels have to be absolutely snapped to voxels. And a lot of voxely engines cheat this, and they allow things to move without being exactly on voxels. If you're willing to allow the entire thing to move by a voxel, then the way you do it is you pre-animate it. You store multiple versions of the object with the stuff moved, and you don't actually allow fine-grained movement. You can do that independently for each 16 by 16 chunk, so you could potentially have a ripple go across the tree by actually changing which ones you update or whatever. There is something in the engine where there is a subset, I think maybe it's currently like 4,000 or so voxels, objects, that when it sees that object ID, or maybe ground chunk ID too, I think it's only objects. When it sees that object ID when it's rendering, it does an extra indirection and looks it up in an animation table. And that actually allows you to have that one object synchronously animate. So all the objects of that type would all animate in sync rather than being staggered and different. But that allows you to update only that little animation table every frame and get big amounts of animation. And that, I think, got coded, because I think at least the data for it exists, but I've never hooked it up to anything. Yeah, so one thing you could always do is in that final step when you're computing the color, you can um, you could take you could store just the distance, how many steps you've taken, and then uh, you um, now take when you get to the end and you're doing all the color processing and everything's in sync and you're not concerned about utilization anymore because you're at 100% utilization. You could then try to recover all the info. You know how far you stepped, so you can take the starting point and that thing and step there, and then you can fetch the voxel data that you need and run through the spans. Maybe you store which span it was, but you'd have to store which object did you hit, which span did you hit, etc. Or you'd have to reiterate through all that stuff. If it's a sparse voxel span, you'd have to, resolve that kind of stuff. So it doesn't make sense to do all that again when you've already done all that work, and you store out more data potentially, right? Like I'm storing, I'll check in a second. I'm storing probably 64 or 128 bits. And you could be storing out how many steps you took, which is like 16 bits. So, and that is going out to an image, so potentially to main memory, L3 or whatever. However, you're in the sparse processing with the rays, that's a write. And writes are kind of free because they just go out and the GPU doesn't have to wait on it. Then when you come back later and you're reading, it's all coherent. You're reading adjacent pixels for all of them. So yeah, and in that testing, if you're not doing a sparse span, all you do is you store where on the span did you hit, how far up or down the span did you hit. You don't figure out what color that is then. You only store that. But you store everything you figured out rather than making you recover that info. So if we look at it, right pixbuff. This does a pixel to vec. Oh, that just stores it. It doesn't actually, I was thinking it might pack it, but it doesn't do any packing. Yeah, so this is what it stores. It stores the height along the thing, texture coordinate info, YPOS, that's probably positioned in the tile as well, actually, so maybe it recovers that. This is a pack of both the X position and the texture coordinate. Oh no, this is a map X position and Y position. So this is the exact location on the map. That's what lets it compute the correct Z buffer. Well, the incorrect Z buffer value is that this lets it get the map position. So you could try to compact this down, not store all of this and recover some of it. But and because it is big, it is 128 bits. But because it's written sparsely and coherently loaded, and it's only loaded once, right? Like, remember, we're doing all this work 3,000 times per pixel, but with the hacky savings of dividing by 32. And that stuff, we work really hard to be efficient. But once you come down to stuff that you do once per pixel, it just doesn't matter. Once you're doing this much work for this other stuff, although 4 milliseconds, obviously it's not that much work. But the whole point is GPUs are super fast. When all you're doing is drawing a pixel and you have depth complexity of 1, and you're not loading lots of textures and doing lots of other stuff, that's totally fine. So having one 16-byte texture that we load effectively, that's totally coherent. We're just totally traversing it in the normal, the obvious order, or an obvious order, as we process the strip and process the rays. And then we have to do an indirection to get the actual ground color or the actual texture color. So we get one real texture fetch and this one very coherent, large, but very coherent texture fetch. It's just not an issue, at least on an NVIDIA GPU. Okay, let me see all these other things that have been, and I'm sorry I forgot to read the question again, but hopefully I said enough to make it clear. Could you do another render with a second camera lower down that looks more face onto the scene, then composite the two? So no, in the sense that this engine can only the fast part of this engine can only render looking horizontally. You can't look down. So it has to do it by rendering horizontally. But like I said, there is a separate shader that does 1 ray per lane instead of 32 rays per lane. And that one can render correctly straight down. But it's not worth it because it's so much slower. And I don't care personally about being able to render straight down. But so like if you had wanted to have a plane or a helicopter that you're flying, and you can go up and then look straight down, and you can be really high in the air and looking straight up down, now you have the problem that every single pixel needs to do a big ray traverse that's looking straight down, and you're not getting the savings of the dividing by 32 from doing 32 rays at a time, because the engine can't work that way. Like the engine is just only designed to work looking, can only get the speed up if it's looking level. Well, and looking level is this weird thing of, as we talked about with the tilting. Yeah, this, where the whole point here is that this camera, it's called view shearing, because and it's also if you know the cameras that have the bellows. So most people may have heard, or some people may have heard, that you can do that crazy tilt shift photography thing with them that lets you get that weird, it looks like a model, the reality looks like a model. But the big thing that those cameras do is they let you have, here's the film in the back of the camera, right? And then normally you have a lens, and your light goes through your lens, and if it's a pinhole lens, the light goes through here, and the image is formed back here reversed. And the idea here is that this is the box, that's the camera. And the bellows gives you fuzzy control of these things so that you can do something like, here's the front of the camera and here's the back of the camera. And so the light rays, and of course the light rays should be bent by the lens, but I'm just like trying to keep it simple. So the light rays do this, and now the light rays will like warp on this. And this isn't super useful, the one I've shown, and the one that is commonly used is to shear it, which, oh, right, I can scroll. There we go. The one that's commonly used is, here's the front plane with the lens, and here's the film on the back. And that means that the light rays do this. And so you capture in your camera a scene, like that, becomes this. And what does that do? What's the good of that, right? It lets you turn the camera without turning the camera. How is that useful? Well, this follows perspective. This is the same as if you took this much bigger image and cropped it. Okay, so here's the thing. Suppose you have a building and you're in front of the building and you want to take a picture of the building. So you tilt the camera up and you take a picture of the building. And when you look at your picture, what do you see? What do you see in your picture? Here's your building. Right? It's in perspective. If you take a view camera, you put it in front of the building, you don't tilt the camera, but you slide the front and the back so that they're like that, then you take this, and the perspective, crazy enough, let's see. So here's the bottom of the building. So here's the door at the front of the building. Here's what you get. You get a building that's not in perspective. Yeah, a lot of the people who do the tilt shift thing cheat it and use post-processing or whatever, but tilt shift is classically done, it was originally done that way. So That's what view sharing lets you do. Is it lets you you're flat, so you're at this level. The whole point here is obviously if you could move up and take the picture of the building from floating in midair, it would be fine. But you can't, so you're at the ground. This is not the same picture you would get if you were up floating in midair, because the internal perspective of things will be different. Like, you know, if there's a inset feature, then the inset feature, if you were floating here, the inset feature would stay perfectly centered. But because you're actually down here, the inset feature does adjust due to perspective, and kind of the internal part of it shifts up or shifts down. Shifts down. So like suppose there's a hole, and then inside the hole is a thing. Now because you're down here, the thing is actually shifted down. Like I should do another box just to be clear. Instead of being, whereas if you were centered, that would be centered. The other thing that you do with view shearing is you do it sideways, like I said. So you put the camera here and the camera here, and you take a photo of a mirror on the wall, and you're, right, this is the lens. And your photo of the mirror where the light bounces and records whatever. So here you're seeing the wall, and here you're seeing a wall, and here the mirror bounces and reflects whatever. In the end photo, notice that it doesn't reflect the camera because the camera is off to the side and isn't visible in the image. But again, because of perspective, the mirror is going to look flat. The stuff in front of the mirror on the mantle is going to look a little weird, like the reflections of them will be shifted. As if you were off to the left. But the mirror itself will look flat, will look like a nice flat rectangle. So that's why people use view shearing in real life using these bellows cameras. And we are using it in the same way for this exact issue. We're saying we have a way to render this thing, and then we recover this image from having rendered that. Because in our special weird camera, we can't tilt it, but we can shear it. So we shear it, and we do this. The shearing trick is actually something that was in the Build engine with Duke Nukem 3D back in the day, and Hexen and Heretic. Because those cameras couldn't tilt in the Doom style engines, they would use the view shearing to sort of fake the effect. It would allow you to look up and down somewhat, but it wouldn't tilt correctly, and people just put up with it. It was okay. Anyway, so that is a little side journey into view cameras. Is that what they're called? And I don't even remember why. I remember reading somewhere that bitwise operations really slow down the GPU. Is that BS? I have no idea. There have been issues in the past where ints weren't as efficient, but at least with GCN, the architecture seems totally fine for it. And certainly my testing with this engine, as I said, I use fixed point for traversing the map as well as the bit operations, and everything seems fine. So if I did the Factorio game, probably, which I'm not going to, but if I would have done it, it would probably have been like with this kind of perspective. So, because it was going to be like a Dwarf Fortress meets Factorio. So there'd be little guys running around. And so you'd probably do something sort of approximating the isometric perspective. And so it would always run fast because it would always be looking down and not drawing out to the horizon. And, maybe you could pull out, it would be city skylines would be what it'd be, kind of like the camera there. So you could potentially tilt it up to look at the horizon. But the normal view, you'd always be looking down, which is good because that's where the fast case, and not out too far where the LOD goes. So that's a thing that this engine could be good at. Did I ever finish explaining why fixing the artifact looking down? Yeah, I did. Okay. But anyway, oh, so yeah, if you wanted to just only barely be able to tilt further down and have the where I currently show artifacts, you could just only render those with the ray traced shader, and it should all line up and work. I haven't maintained the one ray per lane shader. It's not actually quite in sync. Like, it probably doesn't have the sparse voxel stuff, but you could do that as long as it's not too many pixels. It's just the case where, oh, I'm a plane pointing straight down from very high up, that you don't want to do that case. Now, again, being very high up, you're stepping on the map. So like a ray that's pointing straight down just traverses the LOD, the spans in that column, and doesn't do anything else. And the ray that's a little further off only traverses a couple columns before it hits. And the fact that it has to traverse a huge volume of space doesn't matter. But the problem is, once you're high up, out to the edges, you're traversing pretty far in the map. Like if your view angle is 90 degrees, so then you're stepping a 45-degree angle on the sides. So every time you step one voxel down, you're stepping one voxel sideways. So if your altitude is 4,000 voxels, then you have to traverse 4,000 voxels of the map. You don't get the LOD working the same way. Like, you'll need to smarten the LOD because my LOD just currently reduces LOD as you take more steps, and here you need to reduce LOD just on being up really high. It's its own thing, and it's just a mess, and I wouldn't want to do it. Not if you're starting with an engine that is only good at doing flat and therefore limited tilt, basically. Embrace it. And again, like, it can't do bank, and you can work around the banking, and maybe you could try to do the really smart working around the banking, but I would just do the always over, like, because one of the things you prefer is that your frame rate is consistent. So always draw a little extra, crop it out, and then do a little bit of 2D banking as a resample step. Maybe with the existing resample step, but I think it's kind of hard coded to the strips, so I think you'd have to do a separate resample step. I have not gotten any new questions in a little bit, so I can't think of anything else to talk about this. So unless people have questions. Am I still at Rad? Rad got acquired by Epic more than a year ago, and I am still at Epic now. Oh yeah, sorry. The two camera idea where one camera is at the level of the viewer and one camera is lower, that also doesn't work, because now the perspective from the view of that second camera is wrong. Your comment there is correct. I only talked about the case where you put the camera in the same position but pointing straight down or something like that. The idea that if you move it, that just doesn't work, because now the perspective is wrong. The way to think about that, an easy way to think about it, is to think about the rays. The rays have to pass through the eye, or things don't line up correctly, and therefore all cameras must be positioned at the eye, or it doesn't work. Another interesting thing, because this is a ray tracing engine, is if you did that thing about portals that teleport you instantly, you could also actually portal render the thing. Like, you just have to do more raycasts to render through the portals, but they're always limited, right? If you're near the Like you actually can you can teleport the effectively teleport the raycast, right? So you're stepping through the world and you hit the portal, you can teleport the raycast. Now that's really bad when half of the rays hit the portal and half don't, half the lanes, but maybe not that bad. I don't know. Um, and you can also do it the other way. You can say, um, terminate it then and come back later and render just the view. Or you could even, do it render target style. You could say, here's a portal that I think is in view. Let me render through it. If you're really close to it, it's going to be a lot of rays. But if you're really far from it, it's a small number of rays. Maybe it's just one ray job. And who cares if you like, so you've got 30 portals littered around and you don't even know which ones are visible and you just want to pre-render them all. Well, only one, you're only going to be close to one of them, so the amount of extra work you'd be doing wouldn't be that bad. It's better to do the teleporting one. Probably if it's close to you, it's probably better to teleport the rays. um and then, so maybe what you do is like you flag one portal at a time as causing teleportation, and all the other ones you have to pre-render. And that pre-rendering work is wasted if they're hidden from view, but there's only, you only do them out to some distance, and they're always far from the camera, so you don't have to render them with a lot of pixels. Well, there's not an engine I want to put in front of people uh, who think it's general purpose, because it's got all this hard coded tile stuff of, you have to make things with tiles, and it's not a you can't do dynamic voxel explosions, you can't do all that kind of stuff. It's not the kind of voxel engine you'd want. But also, one of the things I was doing with this engine in the early days of working on, because I was working on this at Rad, when I was at Rad, not as part of Rad, is it's like, oh, I can do this incredible amount of detail, right? The whole point was, oh my gosh, at only 4 milliseconds a frame, I have all this really rich detail on the screen. It's all static. I can't really do anything with it, but it's like super detailed and interesting. And the Unreal 5 thing, the detailed polygon thing, frick me, whatever that's called. Nanite, yeah. Nanite basically is like, well, hey, if you wanted to do, like, one thing that people do with like Unreal and Unity, if they want voxel style, is they often don't use voxels. Like Tearaway is real voxels, but a lot of games just they build polygon shapes that are snapped to voxels, and that's good enough as long as you're not pushing the count. And the whole point here was, I was like, I want this really richly detailed super thing that you could never do with polygons. Well, probably you could just throw nanite at it and do polygons, and it would be fine to do the same level of detail that I'm getting in this engine. So if it were still running at 4 milliseconds, I'd see it through. But once I lost that performance, it's just, I don't see the point. It's too many restrictions, not enough performance to be worth it. Yeah, I don't know anything about Unreal really, so I don't have much to say about that. Nanite does do its own compute based rasterization for small enough triangles, yeah. Hardware has generally been pitched as being targeting roughly 10 pixel triangles. They don't try to be super efficient when triangles get really small. And you only have a very limited amount of rasterization hardware parallelism in GPUs. So if you feed it lots of really tiny triangles, like 1 pixel triangles, it can actually be more efficient to write a software rasterizer in compute. This is all public info. There's a public Nanite talk where he talks about this. Well, one thing is if you're just drawing pixels literally, you don't need to use compute. You just use pixel shaders. I mean, it's all GPU compute in that sense, but in the sense of bypassing the rasterizer or whatever, like you draw a full screen quad and you use a pixel shader, and that pixel decides how to draw that pixel. That's a super common thing for the SDF sphere marching demos and stuff like that, where they do just draw a quad or a big triangle or whatever, and every pixel just runs a program that decides how to draw that thing, and as long as they're coherent enough, it works. I mean, you have to be able to mathematically define your thing or whatever. But here, it's this crazy indirection because uh, the the lanes of the GPU do not correspond to one pixel. The it is one ray per pixel, but because each lane is processing 32 pixels, it no longer corresponds to pixel shaders, which is an interesting thing. So in that sense, it is drawing the pixels itself instead of using the rasterizer. But then I do the resampling with a compute shader, but that could be a pixel shader probably. I don't think there's any reason that has to be a compute shader. I think it was just easier for me to share code with the other compute shader. Okay, I don't see any more substantial questions about this engine, so I think we'll stop there. It's almost 5 p.m., so that's the 3.5 hour stream. Thanks everybody for coming along and trying to understand and asking questions and putting up with my terrible drawings and messing up my drawings. And I hope you got some knowledge or enjoyment out of watching. All right, bye-bye.